Welcome to the continuation of the 2023 NASA STEM Enhancement in Earth and Space Science High School Intern Science Symposium. SEAS is a collaboration between NASA, the University of Texas at Austin Center for Space Research. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and been hired by NASA working on missions such as Europa. We are excited to learn about the future accomplishments of the interns of 2023. This year, we received almost 2,000 completed applications and selected almost 200 10th and 11th grade students as participants who were assigned to 18 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work prior to starting their project. Interns heard from 10 NASA subject matter experts during the NASA SEAS Speaker Series that highlighted NASA projects and activities, missions, opportunities, and careers. During the course of this internship, as part of the Speaker Series, you are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller and myself, Margaret Baggio, the managers of this program, welcome to NASA SEAS 2023. Today, we will have 15 team and individual project video presentations. We will divide the afternoon into 2 sessions with one 20-minute break starting at 3:15 Central Time. Project video presentations will either be 5, 10, or 20 minutes in length, followed by Q&A. Please post your questions on the slido.com website and use code SEAS23. Here is our schedule for the day. We will have presentations by teams, followed by a 5 to 10 minute question and answer session. We will invite each team presenting to turn on their cameras and their mics to answer the questions posed by those listening. During the 20-minute break, we invite you to watch highlights of the student intern produced products as part of the Earth and Space Science and Python projects. Our first presentations are by interns in the Mars Rover Utilization team, designed a mission to explore in situ resources utilization on Mars. Key goals included studying Mars habitability, seeking signs of past microbial life, collecting and caching samples, and preparing for future human missions. Interns selected a landing site for a hypothetical rover mission, decided on an instrument payload, determined regions of interest, and plotted a traverse for their rover using remote sensing data of their chosen landing site. Our thanks to S.J. Ralston with Jacobs Technology at NASA Johnson Space Center for their guidance and leadership. So please join me in welcoming the Mars Rover Resource Utilization team and their project investigating the applications of in situ resource utilization for future crewed Mars missions.
Good afternoon. We are the Mars Rover Resource Utilization team, and today we will be presenting water ice and in situ resource analysis at Arcadia Planitia.
Hi, I'm Jackie Law, a junior at Lowell High School in California.
Hi, I'm Simone Henry, a senior at Klassen School of Advanced Studies at Northeast High School.
Hi, I'm Grace, a senior at Adlai U. Stevenson High School in Illinois.
Hi, my name is Annika Sachdeva. I'm a junior at Pinecrest School.
Hi, my name is Jayla Edwards. I'm a senior at Liberty High School.
Good afternoon. My name is Ian Nelson, and I'm a senior at Grace Brethren Junior and Senior High School.
Our mission goal is to send a rover to Mars in order to conduct scientific investigations. But first, we have to understand Mars's background and what we hope to find there. There's strong evidence to suggest that around 3.5 billion years ago, there was liquid water on Mars, and this is when we expect that there was life. Unfortunately, these habitable conditions came to an end as Mars's atmosphere became thinner over time, causing liquid water to boil due to a lack of pressure and making Mars basically unlivable. However, we hope that signs of life are preserved in Mars's ice, which is part of what we hope to send a rover to look for.
Our mission objectives are to determine whether life arose on Mars, characterize the climate of Mars, characterize the geology of Mars, and prepare for human exploration in the future.
So, what is ISRU? ISRU stands for In Situ Resource Utilization, and basically this concept encompasses the idea of using resources that are already present on Mars. This is useful because it reduces mission costs and it minimizes the amount of cargo needed on the initial mission, since resources present on Mars will be used. Since it takes 6 to 8 months to reach Mars and only 40% of missions have succeeded, we feel that in situ resource utilization would be a very useful tool, since planned resupply missions take a long time, and ISRU can be used for material in the meantime to sustain human life for a longer time. Various minerals can be used for infrastructure, fueling, and water ice is essential for life as well to sustain the human life environment.
Mars has many minerals that we could use to establish and sustain a civilization on the planet. For example, minerals such as olivine, hematite, pyroxene, and amphibole could be used in the construction of buildings, roads, and power sources. Oxygen can be produced using the minerals olivine and hematite, and ice could be used for cleaning out toxic materials in the Martian soil, drinking water, and carrying out daily activities. In order to move forward, it is important that we look back to what was done before and learn what doesn't work and what does. For this rover, we looked at 2 missions in particular. The first is the Phoenix Lander, which is the only spacecraft to have landed as far north towards the poles as any other spacecraft on Mars. The second was the Perseverance and Ingenuity helicopter, which proved that helicopter flight is possible and is also collecting samples to bring back to Earth.
Having a rover survive on Mars comes with many challenges. Mars has a thin atmosphere with temperatures that can reach as low as negative 80 degrees Celsius near the polar regions. Also, because Mars is on an axial tilt similar to Earth, it has seasons like winter and summer. We will only have 7 months to accomplish our mission because there's very little light during the winter time. Winds on Mars are also caused by dry ice sublimating along with radiation that can damage the rover's electronics.
So the question is, why did we choose Arcadia Planitia for our rover mission? There was recently a fresh impact crater right near a mound that we chose to look at, and we feel that exploring this area could lead to potential discoveries of ice and of other minerals that are important. And this is also a safer mission compared to looking in the poles because the weather is quite harsh there, and the abundance of ice and minerals is present in the area that we're looking for, so we'll get a very similar result by looking at Arcadia Planitia. Also, for the viability of future crewed missions, we need to find drinkable water, and if we can find a way to extract the water from the mix of regolith and ice, we would be able to use that as an ISRU material. We can learn more about how ice forms at Mars by looking at Arcadia Planitia, and we can also see how rovers would behave in colder environments and potentially send another mission to a polar region in the future.
Next, we're going to talk about landing and our instruments.
What is perhaps the most important part of the mission is landing the rover. The rover uses the same landing procedures as the Perseverance and Curiosity rovers. It follows a 3-step process called entry, descent, and landing, where after entering the Martian atmosphere, it deploys a supersonic parachute to slow its descent. While deploying this parachute, we remove the heat shield, allowing for automated systems to pick the safest landing location, alongside cameras like the MARTI, which captures photos of the landing site and its terrain. After that, the parachute is cut off and they initiate the sky crane maneuver to move out of the way and safely lower the rover. All this paves the way for the instruments to do its job on Mars.
The MARTI, formerly known as the Mars Descent Imager, is a lightweight colored camera placed underneath the rover. As the heat shield is removed during the descent stage of the rover, the camera will record our selecting landed spot. The MARTI is a significant part of landing our rover because imaging data taken will allow our rover to locate the most optimal path for the rover to traverse through loose debris, cliffs, and boulders that can obstruct its path.
Here we see 7 of our instruments as well as the RTG, which we will talk about later. Our rover is called HEF, Hydro Exploration of Frozen Findings, in honor of our wonderful on-site mentor. The first 2 of the 7 instruments are Mastcam Z and Supercam. Mastcam Z is a mast-mounted camera, as its name suggests, that can zoom in, focus, and take high-quality 3D photos and videos. Supercam can tell what atoms and molecules are in a rock from up to 23 feet or 7 meters away, as well as investigate the atmospheric data of Mars. Together, these instruments allow detailed geologic examination of distant objects that may be useful scientifically, but are too dangerous for the rover to approach directly. This helps us achieve the goals of characterizing the climate and geology of Mars.
So how do we keep all these expensive instruments safe? Well, we will use 3 nav cams and 6 HAV cams, navigational and hazard avoidance cameras, to tell the rover where to go and what to avoid, keeping it from bumping into any rocks or getting damaged.
One of our most important instruments is MICA. It is an ice core, which means that it will drill into Martian ice sheets and analyze what elements are in the ice. These represent the atmosphere at different points in time. We can look for biosignatures, signs of life, like methane, which may indicate that there was life on Mars. Beyond that, we can collect general data about what the Martian atmosphere was like long ago. The design of MICA is based off a current drill called Watson, which studies ice on Earth. A diagram of that is on the right of the slide.
The RIMFOX, short for Radar Imager for Mars Subsurface Experiment, is an electronic unit inside the rover that emits radio waves downwards through an antenna attached to the back of the rover, similar to that of a ground-penetrating radar. It provides information about the Martian subsurface by locating water, ice, brines, rocks, and other water-bearing minerals based on how it reflects. By mapping, locating, and collecting samples of these ice deposits with the MICA, scientists could further study them to find evidence of past life on Mars and understand the geology of Mars. To keep track of the weather on Mars, we use the MEDA, more commonly known as the Mars Environmental Dynamics Analyzer. It acts as a weather station that accurately keeps track of the meteorology on Mars using 6 different sensors. These sensors keep track of the air temperature around the rover, so we know when to have a scheduled heating, because near the polar regions it's very cold and it can damage the instruments on board. It also keeps track of the dust in the atmosphere, ultraviolet radiation from the sun, humidity, heat emitted by the surface, direction and speed of the wind, and pressure within the atmosphere, which is all controlled by an instrument control unit. Inside the pressure sensor is a sky camera, which makes calibrated measurements on the brightness of the sun for predictions on solar energy at that location, tracking clouds in the sky and monitoring the dust in the atmosphere. All of these measurements of the Martian weather will be useful for future human exploration of Mars.
Along with the MEDA, SAW ICE is a compilation of 3 powerful instruments, all of which were used on previous Mars rover missions. The Sherlock is a Raman spectrometer that utilizes ultraviolet laser in order to analyze fine-scale mineralogy and organic compounds in high resolution. Sherlock Holmes was a fictional detective who solved crimes. His partner in solving these mysteries was Dr. John H. Watson. Watson, the camera, assists the Sherlock as they solve mysteries about life on Mars. The camera on the Watson is mounted on the hand of the robotic arm, similar to Dr. John H. Watson's hand lens, to magnify and record textures of ice mineral samples that our rover HEF will observe. It also works to identify targets of interest. APXS, the APXS is formerly known as the Alpha Particle X-ray Spectrometer. It will be used on the rover to monitor different ways that water ice and polar regolith respond to X-ray and alpha-ray particle radiation in order to determine the chemical composition of the samples. The RTG, also known as the radioisotope thermoelectric generator, generates electrical power from heat. Heat is produced from the radioactive decay of plutonium-238. The RTG is the most convenient power source for our rover mission because it's lightweight, has a 14-year lifespan, and has been used on previous and successful Mars rover missions. It's also been used in satellites, spacecraft, and lighthouses.
The landing site for this mission is Arcadia Planitia. The region has water ice present and is far enough away from the poles that the rover will not have to handle the extremely cold temperatures found in the polar regions. It is also just outside of the no sunlight zone, so that HEF will not be in constant state of darkness. As well as this, the terrain is flat and has a low rock abundance, which allows for ease of access for our rover.
So here we have an image of the map that we've created for our landing site for the HEF rover. This landing site is between a mineral-full mound and a fresh impact crater to maximize the area that we're going to be exploring. So we'll be stopping at 5 different target sites and potentially a 6th one, depending on how efficiently our rover moves. We have a 15-kilometer landing ellipse, and we'll be using the Sky Crane system by the Perseverance and the Curiosity rover to allow us to land within a small distance to the target 1. So the line outlined in black is our primary mission, and the lines in blue are the extended mission lines after the 1 Martian year, which is when we aim to achieve our goals and we aim to reach our targets. So here we have a graph comparing the HEF mission to previous rovers. Our rover will be traveling 14.01 kilometers, which is more than any rover has traveled in 468 sols. If we use the improved AutoNav systems and the image processing aboard new computers, the rover can travel faster with the autonomous navigation and the autonomous processing. Here we have an image of our first target, and it's around 2 kilometers from the center of our landing site. We have labeled our first target as fretted terrain, meaning that it is a very safe area, and it is labeled Class 1 due to the fact that it's not going to be dangerous for our rover to traverse, and there is a low dust abundance and a low rock abundance. Rock abundance tends to make a rover mission more tricky and more dangerous. This location has a high potential value, meaning that its signature and its heat map indicates a large concentration of a certain compound, and in this case it's H2O concentration that's above 5%. And we plan to use the RIMFAX tool at this target.
Okay. Target 2 is less than 2 kilometers away, and it's a Class 2 land type. Now, we're going to spend about 2 sols here, which is 2 Martian days. And what's so special about it is there's this random outlier of olivine in there. Now, it doesn't mean that there actually is any there, but the characteristics picked up by the Mars orbiter suggest there should be.
So target number 3 is 2 kilometers away from our second target, has dusty terrain, and is labeled a Class 2. As you can see from the picture to the right, it has a high abundance of hematite, which can be used in the production of oxygen and iron for construction.
Target 4 is less than 3 kilometers from the previous site, and it's pretty flat, but we don't have any satellite data in that specific area. So what we did is some data analysis and looked at the stratification of the basalt, as you can see by the light blue mineral colors in the graph. Using that, we can extrapolate about where the next sample should be and the next hotspot should be, which is why we picked this location.
Target number 5 is less than 2 kilometers from our fourth target. It is labeled as a Class 3 because of its rougher regolith. It has a high concentration of H2O, which could be used for ISRU potential, and it could also have a potential to find microbial life.
Hopefully, with all these valuable scientific targets helping create new discoveries, our experiment will have a large impact on advancing NASA's goals for Mars exploration. We plan to look for biosignature molecules with instruments like MICA and SuperCam, which could help produce evidence for the existence of life on other planets and help us understand more about where we, as humans, come from. By using MICA to study Mars's past climate and META to study its current climate, we can learn a lot more about how the Martian climate changes near the poles, helping future human explorers prepare for Mars. With instruments like RIMFAX, SuperCam, and SAW ice, we can learn a lot about Martian rocks and how they differ from other samples in different regions of Mars. And aside from obvious advantages like better climate preparation, we can use information about ISRU materials on Mars to help understand what resources would be available to human explorers in the future, using tools like RIMFAX, SuperCam, and SAW ice to characterize and understand many different types of Martian minerals. This mission will also help pave the way for future Mars exploration, both by rovers and by humans.
This is the initial map we drew out for HEF. And as you can see, it's way too unrealistic. We have to drive around 21 kilometers, which is not feasible with any rover that's currently built today. Its battery life, plus large distances, would cause way too much time for the mission to be completed. So we settled for a much closer mission to the mound.
So here we have an image of our original landing site in a place called Ultimae Scopuli. This location is in the South Pole, and based on Mars Reconnaissance Orbiter imaging, we have pictures of abundant ice in that area. However, there were many problems when looking at this area. We used a database called JMARS, and in JMARS there was a lack of data of rock abundance. This is very important to have due to the fact that a rover must have traversability of terrain. And with a lack of data on rock abundance, we would not be able to know whether or not this area is safe, because the mission that we'd be sending is quite expensive, and we wouldn't want to take any chances by sending our rover to a place where we don't have data. Previously failed NASA missions Mars Polar Lander and Deep Space 2 were actually sent to Ultimae Scopuli, and we still don't have a lot of information about these. And again, there was a lack of data about the essential Mars minerals, which is something that we needed to have in order to send a mission there.
We had a few challenges while researching this project. For example, missing data points in Ultimae Scopuli, as Annika mentioned, and in other places as well. There was hidden power consumption data for the rover that isn't published by NASA for very private reasons. We can't look at classified instruments that JPL has with modern technology, so we have to predict where it's heading next.
I'm very happy I had the opportunity to be a STEM intern, and I'm confident that it'll give me the ability to become an aerospace engineer in the future. I would also like to thank my team and my amazing mentors, SJ, Ralston, and Hef.
During my SEAS internship, I learned the meaning of teamwork and compromise. I'm thankful for my SEAS mentors and teammates who helped me learn about Mars rover and the resource utilization on Mars. In the future, I would like to be an astrophysicist and astronomer, and NASA SEAS is bringing me one step closer towards my goal.
Being a STEM intern has been an honor, and it'll help me pursue my education in computer science.
Coming to SEAS has been an incredible experience, and I enjoyed making friends and learning from my mentors.
I want to be an electrical engineer one day, and I'm thankful for the opportunity that the SEAS internship program has given me. I learned that I love designing experiments and that data research can be pretty fun. I'd like to say thank you to Jackie, love you parents, and thank you Hef, and thank you Ralston.
I want to send my thanks out to Todd Hefflinger and SJ Ralston for mentoring us and giving us their valuable time and allowing us to work as a team together, allowing us to lead in our different ways, and allowing us to grow as students and as people in general.
Congratulations on a great job. We're going to invite all members of the Mars rover team to please turn on their cameras and unmute your mics. We are ready for questions for your team. Our first question is, how many sites did you review prior to your selection?
So we reviewed a couple sites. The main one that we reviewed was Ultimae Scopuli, but we had looked at around 4 sites, including Northeast Eurytus, and a couple other regions that were near the equator. But we had decided as a group to go forward with Ultimae Scopuli, but then as we had talked about in our presentation, with the lack of data available in that region, we decided we needed to move on. So one of our members found a different site, Arcadia Planitia, with a similar abundance of minerals and also an abundance of water ice, which was our main mission to look for. And we had decided as a group collectively that we needed to sort of restart our site searching and really dive into looking at Arcadia Planitia for the rover's mission.
Great. What are other minerals that you are interested in looking for other than water ice? And why are those minerals of interest to this mission?
Yeah, so we did mention a few in our slideshow, but mostly hematite, pyroxene, and a few others, mostly because of their ISRU potential. For example, like hematite can be used in construction and to create oxygen. So we're really looking at things that could help us to put astronauts on the moon or on Mars.
What types of previous missions did you review before making these current rover requirements?
We actually looked at a lot of them. Like we're talking about, there's not that many Mars rover missions because most of them fail actually. Only about 50% get to go. So we were looking at Perseverance, obviously, to see modern technology and how its auto-nav systems work. If you don't know, Mars rovers are using a little bit of AI, a little bit of tracking to figure out how to move certain distances. So we looked a lot at that to see in a realistic amount of kilometers, how far could we travel? We also looked at the Mars Phoenix lander a lot because it scraped a little bit of ice where it landed and then tried to analyze it. There was another failed mission to Ultimae Scopuli, which is kind of interesting because that's where we wanted to check out first. So we really looked at all of them, and we've been looking at a lot of JPL instruments as well that they haven't put on a rover yet that we could use on this mission.
So earliest humans here survived in caves. Did you do any research on caves on Mars as safe locations for dust storms and radiation that might also serve as good storage locations?
Caves definitely would be a great location for possible human explorers. However, rovers really aren't the right way to explore them because rovers do tend to be very large, like usually as big as cars. So it could be hard for them to access the caves. And in addition, rovers usually have pretty strict requirements on like what kind of inclines they can go up and down, and stuff like that, so that we don't damage them. And caves can be very damaging environments. So for a normal rover, caves just wouldn't be a great environment to explore.
And our next question is, will the mica directly analyze any trapped air bubbles in the ice?
So that is one of the MICA's goals, is to analyze air bubbles trapped in the ice that might be indicators of the early Martian atmosphere. So yes, it will.
And how did you fill in gaps in the data when deciding on areas to explore?
We actually tried not to. So when going through all our sites, we actually had to get rid of sites because there was no data. When we're sending a mission to Mars, we can't risk breaking $1 billion+ rover just because we didn't have any data there. That's actually for an orbiter or for another satellite to do, not for a rover. But the one thing we did predict was basalt. So if you look at one of our slides, all our data was pretty consistent. We were able to tell that there's H2O concentration here, there's hematite here. We were very certain of that. But for basalt, we really wanted to test if we could predict where there would be basalt next. So we were able to take essentially data analysis, find all the hotspot streaks and look at the stratification and look at the areas around it. And we were able to predict within 2 to 3 kilometers where the next streak should be. And that's not dangerous. We're not worried about, oh, there's no basalt there, we messed up, the rover mission's over. No, this is actually helping Mars scientists determine if we can predict these structures. So even if we don't get any basalt data there, we've actually learned something, that our prediction models are wrong. So that's good for future missions because we don't have as much data as you would think on Mars.
And is there a coloration between the higher classes of sites and potential water or ice content?
Yeah, absolutely. That's kind of how we had ranked our different sites. But generally during our presentation, we kind of focus on specific minerals at different sites. So we would basically place a site at higher value based on its abundance. In terms of the class 1, class 2, class 3 basically ranks the terrain rather than the mineral abundance itself. So like for the first site, it had fretted terrain, which kind of indicates that the site is a safer place to explore as compared to a class 3 site that has a more rocky surface and has larger layers and hills, which would be more dangerous for a rover to traverse.
You mentioned using electrical power and radioactive decay to power the RTG. Have you thought about also using solar or wind power?
Yeah.
Yeah, so
My bad. You can go.
yeah, so we had considered using solar power, but as we are on Mars, it will be difficult to use solar power as there isn't enough sunlight to reach the Martian poles. So we did consider solar and was it wind power? Is that you said?
Yes.
Okay, so we
Solar
did not
or wind power.
Yes, so we did not consider using wind power, but that does sound very interesting. And maybe in the future, future technology will be developed for wind power harvesting for Mars power sources. That's a very good idea, though. I like that idea.
So Jackie, go ahead.
Also, another reason why we didn't use solar power was because Mars has a lot of dust in the atmosphere, which can like block up the solar panels. And because solar power can only be accessed during the day, it wouldn't be quite helpful since we're near the polar regions where days are quite short during the winter and stuff.
Great. And so the last question, what do you hope to find at the crater in phase 2 of the HEF mission?
We actually hope to find really just what's underneath the Martian layers on the top of the crust. Because what the thing is, you have to understand these instruments mostly can only go a few centimeters down when getting data. So when we have a fresh exposed crater where we don't have to dig anymore, That's actually fantastic because we don't have any data on that before. It's something that's never been done before. There were considerations of dropping a tungsten ball that's 300 kilograms, about 11 kilometers per second, to simulate an asteroid like the heat shield. But instead of doing that, we could just look at a fresh crater and it has what seems like exposed ice. Now, we don't know if that ice is drinkable. We don't know if there's contaminants in it. We don't know if there's air bubbles that signify something really cool about the past Martian atmosphere. So we're really trying to just discover something new, which is what we hope to find with the crater. And it's also not a part of our primary mission. Once we circle the mound is when we plan to head there, because we don't have any data on that area, and we want to play it safe and get our prime mission done, and then check out that cool crater.
Well, great job, Mars Rover Utilization Team. Thanks for joining us today, and thanks for your presentation. We will continue with the Artemis Rhodes team. Artemis Rhodes team modeled their own NASA mission to the moon, including flying to the mission site via drone, surveying the landscape via robot, and taking and analyzing samples. A special thanks to their project mentor, Angelita Crenshaw. Please welcome the Artemis Rhodes team.
Hello everyone, we are the Artemis Rhodes team, and for the past couple of weeks we've been working towards our project in which we've conducted moon, sample, path, and communication research, where we've simulated a rover mission in Shackleton Crater for collection of various samples that will be stored and analyzed. We observed these samples of Shackleton Crater and researched the extraction and applicability of them, concluding with insight into astronaut habitation on the moon in the future. But before we get into that, here's a quick video to introduce the team.
Hi, my name is David Becker-Pearl. I'm from California and I want to major in electrical engineering.
Hi, my name is Evelyn Vargas. I'm from Texas and I want to major in aerospace engineering or astrophysics.
Hi, my name is Sophia Dasser. I'm from New York City and I want to major in computer science and government.
My name is Tyree Gillespie Williams. I'm from Ohio and I plan on studying ecology.
Hi, my name is Manu Doyle. I'm from Washington and I want to major in computer science.
Hi, I'm James Liu. I'm from Texas and I want to major in mechanical engineering.
Hi, my name is Harini Majedi. I'm from Texas and I want to major in computer science.
Hi, my name is Summer Nelson. I'm from New York City and I would like to major in environmental science and finance.
The Interns mission will send a sample collection rover to Shackleton Crater to investigate the crater's composition and the presence and applications of volatiles in the crater. Our mission name, Interns, is a tribute to our destination. Shackleton Crater, located at the lunar South Pole, was named for the Antarctic explorer Ernest Shackleton of the ship Endurance. The Endurance mission patch design was inspired by the Apollo 17 mission patch and the Artemis mission patches. The focus of the patch is the goddess Artemis, whose golden arrow points to a future moon base illuminating the lunar South Pole. The patch also features a golden road in recognition of the Artemis Rhodes program. Mars, seen rising just beyond the lunar horizon, highlights our next goal. Bordering the patch are the names of our 8 team members.
The Shackleton Crater is 20 kilometers in diameter and around 4 kilometers deep at the lunar South Pole, thrice as deep as the Grand Canyon. Due to the lunar axial tilt, the interior of Shackleton Crater is perpetually in shadow, while portions of the rim are permanently sunlit. The crater is a location of interest for future manned lunar missions due to the cold trap created by the permanent shadow, which could potentially preserve volatiles such as ice stores, rare earth elements, and volcanic glass materials all in one area, an uncommon overlap. The sunlit portions of the rim could also provide solar energy to power habitation, infrastructure, and instruments in future missions. In 2010, orbital neutron measurements from NASA's Lunar Reconnaissance Orbiter, or LRO, observed that if lunar hydrogen was in the form of H2O, it would indicate a concentration of 1.5% by weight in the lunar polar regions, including Shackleton Crater. 2018's Chandrayaan-1 mission conclusively confirmed the presence of water ice in regions of the lunar poles, and recorded absorption lines indicative of hydroxyl compounds and possibly of water ice within Shackleton Crater. The analysis of mini RF measurements made by the LRO found that the circular polarization ratio, or CPR, of the Shackleton Crater walls decreased with depth. If ice were the cause for higher CPR readings near the top of the crater walls, we would expect a discontinuity in the CPR gradient at boundaries between seasonally sunlit and permanently shadowed regions of the crater, which was not present. Overall, CPR analysis established an upper limit of 5 to 10% water ice composition in the topmost meter of lunar regolith within Shackleton crater. The albedo of the far side of the moon is 0.22, and the measured albedo of the crater floor was within 0.05 of 0.23. As the albedo of water ice is 1.0, the similarity between the measured albedos rules out the possibility of any single area of exposed surface ice greater than 10 square meters. The Endurance rover mission must therefore confirm the presence of subsurface ice, the most likely form of ice deposit present, particularly within the topmost meter of the lunar regolith on the crater floor. Thus, our rover will be equipped with a drilling tool to extract core samples.
As for reaching the moon, the figure-8 trajectory that we follow may initially appear counterintuitive, but is far easier than traveling in a straight line. The Earth, when we view it from a position above the North Pole, rotates from west to east, much like the moon does, while traveling around the Earth in the same direction. Both the Earth and the moon's eastern edges, which are known as leading edges, face the direction of their momentum. Thus, when a spacecraft performs a gravity assist or flyby, it is influenced by the gravitational pull of nearby bodies. If the spacecraft passes the moon's trailing edge, it receives a significant boost in momentum due to its alignment with the direction of travel. If it flies past close enough with a fast enough speed that it won't be captured and starts orbiting the body, the spacecraft will then be slingshot around and will speed up. If the spacecraft flies past the trailing edge, it gets more momentum as it follows the direction of travel, where on the other hand, passing the leading edge provides a smaller boost. To best execute missions, every spacecraft is launched towards the east, to take advantage of the Earth's rotation and require less fuel to reach orbit. This technique was utilized in previous missions, which changed the orbit from a nearly circular one to an elliptical one, which allows for a faster mission. Passing through the trailing edge would result in the crew being stuck in space much longer, more fuel, and consumables, which aren't in abundance to provide. By changing the spacecraft's path to an ellipse by passing the leading edge, it brings the spacecraft back to Earth without any crew input and allows for a gravitational break. The end result is what Apollo 8's trajectory looked like, a figure-8. And the Artemis 1 mission follows the same basic shape, entering the moon's orbit from the leading edge to perform a figure-8 pathway. To minimize the weight of the fuel needed for the Endurance mission, gravity assist is a major component of the flight path. There is also a natural equilibrium or stability between the orbits of the Earth and the Moon, illustrated by the gravity contours and Lagrange points of the Earth-Moon system. By utilizing this equilibrium in our flight path, we can further reduce the fuel needed for our mission. Once our rover has reached the Moon, it will enter into a near rectilinear or halo orbit around the Moon with respect to Lagrange point 2, giving us optimal access to the South Pole. Once over Shackleton crater, entry, descent, and landing, or EDL, will commence.
Part of Endurance was to design a model rover to explore the Shackleton crater and to obtain samples in order for further analysis of habitation on the Moon. In order to best simulate the mission, we designed our entire robot under two principles: to simulate accurate crater conditions and to minimize the contamination of both the sample and the surface of the Moon. While designing the robot, we employed a 4-step design process, including brainstorming, research, CAD, and iteration on each mechanism to efficiently build and test components for continuous improvement. For the chassis, the biggest challenge was to be able to easily maneuver the surface without risking tilting and falling over. As a result, we decided to implement a suspension system on our base. In our initial design, we implemented a pendular suspension system that only provided one axis of rotation horizontally. This proved to only work 17% during testing due to not providing vertical movement and getting stuck while moving up a structure. Rev 2 provided a swing axle suspension system which allowed for more vertical mobility and increased the success rate to over 90%. Our first claw design used a direct one-on-one gear train. This design proved difficult to both attach a motor and effectively secure the core sample. To solve the motor attachment problem, we added a bevel gear to the claw. However, this attachment made the claw asymmetrical and therefore difficult to attach to any type of lift. Our third rev of the claw added 2 beams in order to better secure the sample. However, the sample could not maintain a consistent position every time. Rev 4 used worm gears and had an aligner for the sample to be pushed onto every time. This allowed for not only a larger grab radius, but also consistent grabbing positions. To reduce contamination of the sample, it is important to lift the sample. Our initial design was a parallel linkage system. This design did not allow the claw to be parallel to the ground, which made the claw change the grab angle virtually every time. To make the lift more consistent, we tried a linear slide. The slide, however, took up too much vertical room, and the lowest the claw could go was actually 6.35 centimeters. Rev 3 was similar to an elevator mechanism. However, instead of pulleys, we used worm gears. This allowed for 100% consistency in vertical movement. However, similar to Rev 2, it took up too much vertical room. Our final design was an improved linkage system that provided 3 axes of rotation. This allowed the claw to move parallel to the ground and maintain the same orientation throughout the entire lift process.
Although we tried to make our model as realistic as possible, building out of Legos and time constraint limited us from adding multiple features that we would add on a real rover. For one, we wouldn't be able to use regular tires due to several differences in the moon's composition, such as its atmosphere, surface, and gravity, which would cause regular wheels to break, reduce traction, and several other consequences. As such, we would want to use metal wheels similar to those of NASA's Viper mission, as seen in the video to the right. We would like to acknowledge Ms. Emily Soden from NASA's team on the Viper mission for her support and invaluable contributions to our project.
In the video to the right, you'll be able to see our model rover collecting the model samples on the moon. Another important factor to consider in a more realistic design for the rover is the power source. Solar-powered batteries such as those seen on Viper would not be feasible due to Shackleton Crater's size. The rover wouldn't be able to explore in depth if it had to periodically return to the surface to recharge. As such, we would opt for a radioisotope thermoelectric generator, such as the one found on Perseverance, to be able to power the rover for an extended period without access to sunlight. The Artemis rover would be controlled through a mix of autonomous and human control. Unlike the Mars missions, which send overnight instructions for the rover to complete during the day due to signals taking multiple minutes, Moon rovers can receive signals within seconds. This would allow the rover to receive human commands more frequently and would even allow them to remote control it. As such, the rover software would include both an artificial intelligence system allowing the rover to complete tasks on its own, as well as the option for specific commands or remote control. The rover would also have a mechanical drill to drill into the ground and extract the sample. To store the samples, we would drill out a cylindrical chunk and pack it into a tight container to avoid any movement of the sample in order to keep the sample intact. To determine where to drill, the rover would use existing satellite data on the levels of hydrogen, thermal mapping, radar pulses, and near-infrared light reflection in order to determine the most likely locations for where water is found. Although the end goal would be to return the samples extracted from Shackleton Crater to the Earth using a full lab, the mission would still have a small lab within the rover to be able to analyze the composition of the samples.
In order to find a path that was suitable for endurance, one must be familiar with the geography of Shackleton Crater. After studying topographical and geomorphic maps, it was found that the rim of Shackleton is littered with deep banks and slopes known as scarps that could drop as low as 10 meters. In order to mitigate damage to the rover as well as any samples it carried, the rover will land in a spot free of as many scarps as possible.
Communication between the Earth and the Moon is an important thing to consider as we venture further into the realm of cislunar travel. Because of the relatively close proximity of the Moon, all communications to and from our rover will have a delay of about 6 to 10 seconds, as opposed to the 20-minute delay in communications with Mars. During the Apollo era, line-of-sight communication was the prevailing communication method, but continuous communication between the Earth and our landing site at the lunar South Pole, as it stands, is impossible, and poses a major problem for future lunar missions with the possibility of hours-long communication blackouts. Communication is vital to space exploration, for Earth-based support in both manned and unmanned missions where unexpected or unanticipated obstacles inevitably arise. The lunar South Pole, the target of the proposed Endurance mission, is rugged. Line-of-sight communication will be affected by high obstructions such as crater walls, rocks, etc. Additionally, as the Moon rotates, it will itself become an obstruction to communication. Thus, our rover will relay its communications to the Earth through the Lunar Reconnaissance Orbiter, LRO, when line-of-sight communication is impossible and the LRO is overhead. This solution is only short-term and suitable for the purposes of this mission, though future lunar missions of larger scopes must consider the development of reliable lunar communications infrastructure, much like that of the Earth.
The South Pole, and specifically the Shackleton Crater, contains an overlap between creep, volcanic glass, and ice materials. Hence, it is the best place to collect samples from. The few known pristine creep rocks are basaltic lavas. Basalt results from the rapid cooling of molten rock from extensive lava flows. As visible in the figure, creep basalt contains high contents of various rare earth metals in comparison to other low Ti aluminous basalts, displaying the relevance of analyzing the samples for future rare earth metal extraction on the Moon. To allow for long-term human presence in space, the extraction of extraterrestrial raw materials known as in situ resource utilization is required to eliminate the need for shipping such resources or manufacture materials from Earth. The 5 most beneficial areas of ISRU for future robotic and human exploration are resource characterization and mapping, mission consumable production, civil engineering and surface construction, energy generation, storage, and transfer within in situ resources, as well as manufacturing and repair using in situ resources. In addition to hydrogen and oxygen utilization, the extraction of rare earth metals from lunar samples is currently being explored. CREEP samples, which is an acronym, K for potassium, rare earth elements, REE, and P for phosphorus, are of important interest. The content of uranium, thorium, neodymium, and other elements within these samples is highly valuable due to the increased demand and limited opportunities for rare metal reusage. Rare earth metals are one of the main components of the communications and nuclear energy industries, as well as the construction of electric vehicles. In terms of nuclear power of lunar vehicles, uranium and thorium could hypothetically be extracted and used to power said vehicles.
The second sample is the lunar troctolite. The lunar troctolite is a rock type within a group of ultramafic platonic rocks from the moon known as the MGSU. This rock type contains volcanic glass and lunar apatite beads, which can show evidence of pre-existing bodies of water on the moon through analysis and connection to the lunar magma ocean. Understanding the moon's magma ocean in depth could help us understand the development of Earth's. New techniques such as secondary ion mass spectrometry were employed to examine hydroxyl, fluoride, and chloride in apatite samples from 3 distinct lunar sources. As seen in the figure, the method of measure validates the existence of significant amounts of water in the form of hydroxyl. What can the glass beads tell us? In Figure 1, it can be seen that there are significant correlations between the volatile contents measured for the very low titanium glasses. In Figure 2, the sharp decrease in volatile content from core to rim suggests that the volatile contents are indigenous to the moon and were affected by degassing during magma eruption. Computational simulations that consider the degassing suggest that there is an estimated water content of 745 parts per million at a 95% confidence level. From the analysis of these volcanic glasses, the possibilities are endless. Remarkably, we can learn about the origin of Earth's plate tectonics and water by comparing Earth's delayed plagioclase crystallization, which is related to magma ocean composition, to that of the moon. The moon is ideal for this analysis because of its preserved rock record due to the lack of erosion, atmosphere, and plate tectonics. Our team would like to thank Dr. Tab Preisel of the JSC for all of his guidance during our research journey. Our third and final sample is the ice core sample. When we obtain our ice core sample, our drill and container must be composed of steel, Teflon, and aluminum in order to avoid sample contamination. One of the most astounding discoveries from Clementine and Prospect, 2 rover missions that explored the lunar South Pole, is that within the South Pole Aitken Basin, there are permanently shadowed areas that possess sufficient environments to accumulate frozen volatiles in the cold trap. Deposits of ice on the moon have many practical aspects for future manned lunar exploration. There is no other source of water on the moon, and shipping water to the moon for use by humans would be extremely expensive, possibly $2,000 to $20,000 per kilogram. The lunar water could serve as a source of oxygen and hydrogen, which can be extracted and used for rocket fuel or breathable air. Paul Sputis, one of the scientists who took part in the Clementine study, referred to the lunar ice deposits as possibly the most valuable piece of real estate in the solar system.
When it comes to a mission as paramount to human discovery as this, it is imperative that the astronauts with boots on the ground get everything they need to survive and thrive on the moon. Ideally, an astronaut's needs in terms of food, water, housing, health, and communication with mission control will be accommodated for on the moon. Prepackaged foods, hydroponic systems, and systems for recycling waste into clean water similar to that on the ISS are a good place to start when thinking about food and clean water. Much similar to how Artemis 3 has been planned, our astronauts will be housed in or near the landing system they came from, and from there, communicate with mission control and complete tasks. Isolation from Earth is definitely stressful, so regular communication with loved ones and mental health professionals is a must. Measures also need to be taken in order to minimize medical emergencies through regular deliveries of medicine and mandatory first aid training for all astronauts.
Thanks to SEAS, I found a supportive and ambitious STEM community.
Because of SEAS, I want to pursue undergraduate research opportunities in STEM.
SEAS has really taught me the importance of the design process in everyday life.
My experience at SEAS has further inspired me to pursue my goal of becoming an astronaut.
SEAS boosted my confidence in communicating and working with others on projects.
SEAS has made me realize how interdisciplinary space science is and has given me lifelong connections with people all over the country.
SEAS has allowed me to explore the abundance of career opportunities within engineering.
SEAS has encouraged me to continue pursuing computer science and continuing research in aerospace engineering.
We would like to extend a thank you to NASA and the Center for Space Research for hosting the NASA SEAS program. We would also like to thank Dr. Emily Certain, Dr. Alexandra Mateli, Dr. Tab Preisel, Dr. Susanna Foxworth, and our dear mentor, Ms. Angelita Crenshaw, for their guidance and expertise. Special thank you to Mrs. Selena Miller and Mrs. Margaret Baggio for organizing the NASA SEAS program.
So great job to the Artemis Rhodes team. We invite each of you to turn your cameras on and to unmute your microphones. We have several questions that have been posted in the Slido app. Our first question is, will the samples be sent back to Earth for analyzing, or will they be analyzed on location?
Yeah, I'll take that question. It's a really good one as well. During our team's meeting with Dr. Tab Preisel, we actually discussed this exact idea, and ideally we want the samples to be analyzed on the rover, but realistically we simply don't have the tools for it yet. And so our team solution was kind of to do both. Analyze the solutions, analyze the samples directly on the rover with the tools that we can, whether that's using microscope pictures of the samples and trying to understand the composition on the rover, but then also sending them back to a lab on Earth and getting into like more specific research of the samples.
And the next question is, how did you divide up parts of your project to ensure that you were optimally successful?
Okay, I can take this question. So the communication is like a super important part of this project. So in the first day, we had like a really big whiteboard meeting where we just split our mission into two major parts. First is the research part, and there's also the rover design and drone flying part. So basically, we also divided the two major parts into subparts where there is, on the research side, there's stuff like sample research, communication research, and a bunch of small topics. And everyone that was interested in a specific topic, can choose basically what they wanted to research. And then on the robot building side and the drone flying side, anyone that had a little bit of prior experience, anyone that was interested could participate in that part. And then after every single session that we had a like a 10-minute, 20-minute session with all of us together. And that way we could communicate what we had achieved, what our goals were for the next session, what we wanted to do next session, and just the status of how everything is going along. So that way we could maximize our efficiency and to get optimum success.
And the next question is, what do you think is the most difficult aspect of this mission?
I can take that question. So I would say that one of the most difficult parts of the mission, the proposed mission to Shackleton Crater, is definitely the communications problem, because with Apollo, communications were comparatively much easier. And the whole problem of communicating with the Earth is a problem that none of us had really considered before we started working on this project, and is definitely something that must be solved going into the future with Artemis, especially whenever astronauts eventually establish habitats on the moon, because it's not only important to the mission itself in order to get the mission done, but it's also important for the astronauts' mental health, because they have to be able to communicate with the people back on Earth. So I would say that communications is a big thing that we need to overcome.
And did team members already have drone and robotics experience prior to SEAS?
Yeah, I'll take that question. So I know personally from my experience, I do participate in my school's robotics club, and I know that James also participates in his school's robotics club. And then in terms of like drone experience, um, I had some experience flying drones, but I think none of us had a lot of experience. So it was definitely a new thing, and to test that.
So if you still had more time working on your project, what's one thing you would want to research?
So on the mechanical side, the major thing we would like to research more about is suspension system, because currently our suspension system on our Lego model rover is I'm not sure how well it will do on a different type of different gravity. So we would like to definitely research more on different suspension systems, the pros and cons of each suspension system, and which suspension system would actually work best on a lunar gravity.
And on the research side, we wanted to look more into like the different other kinds of volatile samples that we could be collecting and more applications. We had very like minorly dabbled into kind of the applications of volatile samples, but we definitely want to do more research and experimentation if possible with that.
Well, great job. Congratulations to the Rhodes team. So the GRACE team analyzed data from the Gravity Recovery and Climate Experiment and GRACE FO, twin satellites that are making detailed measurements of Earth's gravity field changes and revolutionizing investigations about Earth's water resources over land, ice, and oceans, as well as earthquakes and crustal deformations. A special thanks to their project mentors, Chirag Patel and Chang, for their guidance and dedication. Please join me in welcoming the GRACE team.
Good afternoon. Today we'll be talking to you about mass loss estimation of polar ice sheets and global sea level change using predictions made from GRACE/GRACEFO data. Our discussion will centralize around 4 points. Background information. We will discuss prevalent information concerning the regions of Greenland and Antarctica on the subject of climate change, introduce information on the GRACE/GRACEFO satellite that we collected data from and used to create our data projections. We will discuss the purpose of our research, explore the usage of data and general patterns identified, provide a display of all translated data into graphs to show data trends over time, such as a map presenting the effect of mass change on rate acceleration, loss of liquid water equivalent thickness in the basins of Greenland and Antarctica, LWB, and its contribution to sea level change. And finally, we will show future predictions. As the public is well aware, the regions of Greenland and Antarctica ice sheets have garnered significant attention over the years. We observe here major newspapers like Washington Post, CNN, and USA Today publishing articles discussing the subject and directly naming sea level rise as an issue. The mass ice sheets of the Greenland and Antarctic region maintain responsibility for almost a quarter of the world's ocean sea level rise. Polar ice sheets account for approximately 99% of Earth's freshwater ice on land. The gradual mass loss of the ice sheets is substantially contributing to changing sea levels worldwide. Our investigation delves deeper into the intricate process of ice mass loss in the polar regions, aiming to enrich public understanding and contribute to the urgent global efforts to tackle this issue.
In 2002, GRACE was launched. The Gravity Recovery and Climate Experiment mission flew twin spacecraft in tandem around Earth to study key changes in the planet's waters, ice sheets, and solid Earth. It measured month-to-month variations in gravity, changes in the distribution of mass, and water movement. The data collected from the satellite helps scientists understand processes like ice melting, sea level rise, and groundwater depletion. Exceeding its supposed 5-year lifespan, GRACE lasted 15 years, and as the acronym suggests, GRACEFO is the follow-on of GRACE, which was launched in 2018. The GRACEFO mission is a partnership between NASA and the German Research Center for Geosciences, in efforts to continue the high-resolution monthly global maps of Earth's gravity field and surface mass changes of the original GRACE mission. Continuing the discussion of GRACE in application to our data, it is important to discuss the laser ranging interferometer and the K-band ranging instruments, as they provided substantial data to our study. The Laser Ranging Interferometer, or LRI, was an add-on to the GRACE-4 satellite which uses laser interferometry to precisely measure distance fluctuations between the two GRACE spacecraft. It is where we get our Laser Range Acceleration, or LRA, data from. The K-band ranging instrument, or KBR, also referred to as the microwave instrument, is also on board the twin satellites, pointing microwave instruments at each other to obtain data on distance changes. This is how K-band range acceleration, or KRA, raw datasets are obtained. The questions our research aimed to answer were: how can we use GRACE follow-on data to estimate mass loss in the Greenland and Antarctica basins, and how can we project these losses to see the effects on global sea levels? Our study was a centralized effort to explain the data produced by GRACE and GRACE-4 in the concentrated basins of Antarctica and Greenland, and map data to show changes in sea level globally. While working on our research, we utilized the LRI and KBR data collected by the GRACE-4 satellites. The data is used to produce mass change over mass concentration blocks, or mascons, which are discrete cells located across Earth's surface with their mass change signals. We were able to mass these mascons over Greenland and Antarctica, and finally, calculate the basin averages for Greenland and Antarctica over time and measure the impact of those mass losses on sea level change.
Using GRACE and GRACE follow-up satellite data between 2002 and 2023, we estimate the present mass loss in polar regions and project future shifts in sea levels around the world. Instruments on board measure the inter-satellite distances, which provide raw range data from GRACE and GRACE follow-up. The range data can be converted to gravitational potential data, then to data about mascons in terms of LWE, or liquid water equivalent, and finally to sea level data. GRACE follow-up satellites are in a circular polar orbit, meaning that each satellite passes over both poles during each orbit. The visual here shows the satellite's ground track, or the path GRACE takes over Earth's surface. The upper left shows a ground track over 1 day, the bottom left shows a ground track over 10 days, and the right shows a ground track over 30 days. Over 30 days, GRACE covers substantially more of Earth's surface compared to the previous ground tracks. This is approximately covering the entirety of the Earth, and this is why we use monthly data to establish each mascon solution. Due to gravity, when GRACE goes over a larger landmass, such as a mountain, the gravity pull increases the acceleration of the first satellite, and the range between the satellites increases until the second satellite reaches the mountain, as shown by the image on the left side. Once the second satellite reaches the mountain, the acceleration of the second satellite increases, and the distance between the twins decreases. Using the two instruments onboard GRACE that we mentioned in the previous slides, we can use these distance fluctuations between the satellite to measure the gravity pull on the satellites, because it directly correlates with the acceleration. The range rate, and range acceleration graphs on the right side demonstrate the change in distance between the twin satellites as they travel over larger land masses like mountains. A peak-trough peak in range acceleration corresponds to a positive mass, and a trough-peak-trough implies a negative mass. These graphs show how the range rate is derived from the range, and how the range acceleration is derived from the range rate. Both GRACE and GRACE follow-up include a microwave instrument that has a range measurement accuracy of 1 micrometer, which collects KRA data. However, GRACE follow-on tests a new instrument called the Laser Ranging Interferometer, which has a range measurement accuracy of 10 nanometers, and is more accurate by a factor of 100. On the left, we demonstrate that over a December 2020 pass, covering half the Earth's circumference, with range acceleration data from both KBR and LRI, we see that there are fewer fluctuations in the green LRI line compared to the red KBR line, because the LRI data is less noisy, meaning that it is more accurate. On the right, the map we created on this slide shows a range acceleration observed during a pass of GRACE follow-on's polar orbit. To demonstrate the previous slide's range acceleration pattern, towards the bottom and top of the graph, we see a trough-peak-trough on both, which illustrates the mass decrease in Greenland and West Antarctica. Here are the residual range acceleration geographical graphs for December 2020 that we created using GRACE-4's instrument data. Using the two instruments on board GRACE-4 we discussed earlier, KBR and LRI, we receive raw residual range K-band and laser range acceleration, or KRA and LRA. We discussed how KBR is less accurate. It can also be seen on these geographical maps too. At first glance, the two global charts may seem the same, but looking closer, the LRA has fewer splotches of irregular data than the KRA, especially seen over the ocean. Additionally, the large fluctuation patterns in the water that we talked about on the previous slide are depicted here. When you see a drastic red-blue-red color pattern or blue-red-blue pattern, it signifies a change in the gravity pull of that area on GRACE, demonstrating a water mass or water shift in that region. For instance, North Canada and some parts of Antarctica are gaining mass because GRACEFO is detecting mass gain at red-colored regions that are surrounded by blue-colored regions. In West Antarctica, however, the large red-blue-red pattern demonstrates the significant ice mass loss in that region. From the visual, we observed the large correlation in patterns in Greenland and Antarctica. This is why we chose to focus on the regions, which we will discuss further in the next few slides.
Based on the aforementioned association between KRA, LRA, and mass change, we can derive the monthly mass-con change grids over the globe. The mass-cons are quantified in terms of liquid water equivalent, or LWE. LWE is a way of representing mass changes over a mass-con in the unit of water thickness. For example, if 1 centimeter change in LWE in a certain mass-con is like saying that mass has been added to the cell equal to water spread out over the entire mass-con 1 centimeter deep. We distributed the data amongst 3 regions: Greenland, East Antarctica, and West Antarctica. These 3 regions were separated due to different geological situations affecting each region. The mass-con datasets we are using are split up by months starting from GRACE's launch in 2002 to GRACE-FO's current operation to 2023, which is approximately 219 datasets that we've worked with. From the mass-cons blocks for Greenland, West Antarctica, and East Antarctica, we computed Bayesian averages and derived the mass change time series for each of the 3 regions. From the data, we calculated a least squares regression line to approximate the LWE thickness change per year from April 2002 to March 2023. West Antarctica and Greenland showed a decrease in LWE at negative 4.87 centimeters per year and negative 10.8 centimeters per year respectively, and East Antarctica showed an increase in LWE at 0.479 centimeters per year. From the LWE data, we were able to convert this mass to mass change with a conversion that used the area of the specific region and the density of the water. So we measured mass change in gigatons, which is equivalent to 1 billion metric tons or 2.2 trillion pounds. So what does a gigaton look like? So currently we're looking at a graphic created over Central Park in New York City. And currently we're visualizing a gigaton of ice. And it will be over Central Park, it will be that height and that big over Central Park. So, yep. So our computation suggests that West Antarctica and Greenland are losing mass at approximately negative 105.1 gigatons per year and negative 233.7 gigatons per year respectively, while East Antarctica is actually gaining mass at 31.5 gigatons per year. Over 21 years, the average rate of ice sheet mass change was approximately negative 307.3 gigatons per year over the 3 regions. Overall, the ice sheet mass loss contributed to a global mean level sea rise.
From the time series of mass change of the polar regions, we derived time series plots of their contributions to sea level change by using the total area of the world's oceans. As more mass is lost from the polar regions, it contributes to a positive sea level rise. Deriving the slopes of the time series plots, we intend to find the average contribution to sea level change from each polar region. With these rates, we intended to project the sea level changes for the next 100 years by combining data from all polar regions.
Sea level rise due to polar ice mass loss is not uniform. Looking at the left image on the slide, we can see the ice melts from the dashed black line to the dashed red line. As the ice melts and transitions into the water level experiences a decline due to the associated mass loss. Consequently, this reduced mass induces a diminished gravitational pull in the immediate vicinity. This mass redistribution has a border effect, leading to a noteworthy phenomenon in near-field geographic regions. In areas near the mass loss region from the initial ice melting,
the water level undergoes a rise, accompanied by crust deformation, and the crust uplifts and results in an action similar to a decrease in sea level. In the image on the right, it's apparent that as the ice sheets lose mass, the rotation pull of the Earth can also change, which also contributes to the change of water distribution on Earth, which can result in changes in weather patterns. These effects are known as GRD, or gravity rotation and deformation. Based on these effects, we can compute a global mean sea level fingerprint from GRACEFO and compute a map of how melted water will redistribute globally for each ice sheet or region. In West Antarctica and Greenland, our mass change plots had negative slopes, and their sea level rise plots had positive slopes, so their mass loss resulted in a contribution to sea level rise. However, in the region of East Antarctica, it's observed that this region has an increase in ice mass. This projection, unlike the ones of Greenland and West Antarctica, actually results in a decrease of sea level rise. As shown on the graphs, the sea level contributions from Greenland and West and East Antarctica are different depending on the region. For example, Greenland's sea level contribution is more prevalent in the Atlantic Ocean, while West Antarctica's sea level contribution is more prevalent in the Pacific and Indian Oceans. For this final plot, we combined the graphs and data from all three polar regions for sea level change and constructed a map to illustrate predicted sea levels for the next 100 years. Over 100 years, we projected that the global ice sheet mass loss will contribute to an average sea level rise of 85.1 millimeters. Sea level fingerprints have shown that ocean fluctuations are not uniform and vary from region to region. On average, water levels further away from the poles increase, while water levels closer to the poles decrease. While the Pacific, South Atlantic, and Indian Oceans are projected to rise more than 100 millimeters in sea level, as compared to a global average of around 80 millimeters, the Southern and Arctic Ocean sea levels are expected to decrease over the next century. For the coastal regions of Hawaii, Tuvalu, India, and Yemen, to name a few, rising ocean heights are an apparent issue. As we begin to address the complex rising sea levels problem globally, interdisciplinary efforts are essential to developing sustainable and innovative solutions that can protect vulnerable regions while fostering global cooperation to combat the impacts of climate change. Here are our citations.
Thank you so much for listening to our research presentation. We hope this was informative and insightful. We'd like to give recognition to the NASA SEAS internship program for this opportunity as a team to conduct authentic research, the CSR facility for their generosity to provide us with a working environment with incredible resources, and lastly, our amazing mentors Chow Young Zhang and Chirag Patel for their endless patience, energetic experience, and undivided desire to teach us. Thanks for listening.
So congratulations to the GRACE team. We'd like for you to please turn on your cameras and unmute your microphones. We have several questions for the team. The first question is, do you have any thoughts on why Eastern Antarctica is gaining mass ice?
So currently what we see in East Antarctica specifically is that over the past 10,000 years, we saw snow accumulation on it where the precipitation falls onto East Antarctica and more mass is gained. But however, there are still ice glacier mass loss in that area, but this mass accumulation through the snow that's falling on East Antarctica is actually outweighs the mass loss in East Antarctica. However, in the general West Antarctica and Greenland combined, this doesn't really mean that there's that much gain in mass. It still has a lot of mass loss. So, yeah.
And do you, what was the most interesting fact that you discovered while conducting research on your project?
I can take this one. I think the most interesting fact was the fact that East Antarctica did gain mass, because going into this, we assumed that most of the polar regions would have mass loss, so ice loss, and sea level would rise there. But East Antarctica surprised us in that they increased ice mass.
And could someone explain the twin satellite configuration used by the GRACE mission and its importance or significance?
So basically, Grace and Graceful are both twin satellites that measure the distance between the two satellites, and there's like a couple of instruments they use, like the microwave interferometer or like the laser ranging interferometer. So it can detect these changes between the distance with like really high precision, and it can also do it better than just like if we only used a single satellite. And the importance of this is that whenever there are like fluctuations of the range between the two satellites, we can use that data to kind of see what kind of mass change is occurring, because the fluctuations mean that the force of gravity that Graceful is traveling through is like not exactly uniform, which means that there must be some kind of mass change happening.
And can you give an example of what the potential impact would be on sea level rise on areas like Hawaii, or let's say the Florida coast or something like that?
I guess I'll take this one. So currently what we see that's happening with all the data that we found in our calculations, there would be heavy sea level rise in those regions, specifically in the Pacific Ocean near where Hawaii is, as well as the Florida coastline. So sea level would drastically rise in these areas within the next 100 years and continue to rise in the future as well. So it would be drastic for the economies, the territories of people who live there and function off of fishing, wildlife, and logging and things like that. So it would be very drastic for the economies in the countries that are there.
Well, congratulations to the Grace team. You've done some excellent work. The Mars exploration team investigated the infrastructure on the Mars planet's surface that is necessary to sustain the first cruise. This includes power, habitation, water, food, health maintenance, mobility, emergency care, and scientific support functions. Using basic engineering design principles, Interns designed a Mars village that will allow people to live and work productively and safely for up to 1,000 days on the Martian surface. A special thanks to Adam Noakes for his guidance and commitment to the Mars exploration team.
Mars has captivated the interest of humanity ever since the bright red dot was noticed in the night sky. Hello everyone, we are the 2023 SEAS Mars Exploration Team, and we present Drive Home, devising research initiatives for venturing and establishing a habitat on Mars for exploration.
Hi, my name is Quinn Brown, and I am a rising senior from California.
Hello, I'm Soren Fine. I'm a rising junior from Los Angeles, California.
Hi, my name is Tina Lee, and I am a rising junior from Anahuac, Texas.
Hello, I'm Varsha Makapati, and I'm a senior from Ellicott City, Maryland.
Hi, my name is Aditi Radhakrishnan, and I'm a rising senior from Raleigh, North Carolina.
Hello, my name is Aiden Schneider. I'm a rising senior from Reno, Nevada.
Throughout this 2-week internship, we've had the opportunity to work with Professor Adam Noakes from the University of Texas at Austin. His extensive knowledge and genuine passion for future space exploration continuously inspires us every day.
So why Mars? Mars shall be explored and inhabited for the Earth-wide realization of humankind's capabilities. This systematic exploration includes a scientific approach to experimentation in an adverse environment, creating a sustainable way of life, and emphasizing the search for life.
One of the most important steps in designing a Mars mission is determining where the mission will be located. There are several criteria that a potential site must meet, including flat, even terrain, a scientifically interesting environment, access to underground water ice, and preferably already available information about the site from previous missions. While any location on Mars would be an amazing opportunity, some locations stand out as superior. These include Acidalia planitia, a large region once part of Mars's northern ocean, Arabia Terra, a volcanic area bordering on Acidalia, and Hellas planitia, a large impact crater in the south that is the planet's lowest point. However, the location that we have chosen is Chryse planitia, a large basin to the south of Acidalia planitia. As you can see, the specific site of the outpost will be on the far eastern side of Chryse, just to the south of Aedes Fossae. Chryse planitia is the perfect location for our Martian colony. The area's terrain is smooth and contains a manageable amount of rocks. It was once an ocean and contains volcanic debris and outflow channels such as Nicolaris mensae, a few days' drive from the landing site, which makes it a region of significant scientific interest. It is located at the latitudes predicted to have ice at shallow depths, and the Pathfinder and Viking 1 landers which landed there gives us useful information about the region's conditions.
Mars Ascent and Descent vehicles serve as a gateway between the crew and the outside world. Minimizing MDAV weight is a priority, so we limit flights to less than 24 hours, prestage all habitat structures, and employ a 2-stage liquid propulsion system. To ensure a safe landing location across multiple missions, we utilize a binder regolith reinforced landing area and an anchored carbon fiber fabric barrier. This mitigates dust ejection and provides a level landing surface. Each module consists of an inflatable liner, a 3D printed radiation shield, and a geodesic truss-based shield. The inflatable liner is made of hydrogenated plastic and features 4 multi-gravity active mating adapters, maximizing the viable connections to other habitat elements. All 4 adapters can be flat-packed for space-efficient transportation. The liner offers both opaque protection and skylight-style windows. Its rounded top protects the inflatable from dust accumulation. Martian regolith is used for radiation shielding in the module's 3D printed cylindrical shield and tiles, fastened to its geodesic truss. During pre-staging, rovers position the liner, the Icon 3D printer prints the radiation shield, the liner inflates, and the triathlete robots assemble the geodesic truss structure, all autonomously. On arrival, the crew inspects the truss, guides the final tightening of the structures, and places regolith tiles into the trusses, adjusting liner pressure as needed for successful implementation. Modules are each designed to house 2 crew members. One science module is dedicated to a human research and biology lab, while geology and physics labs are housed in another. To isolate potential biohazards, one module is a dedicated medical area. One module would be dedicated makerspace to enable easy maintenance and isolate foreign object debris. The final science modules will house a system control center as well as a greenhouse. The same open source adapter is used for all module-to-module connections. We provide both short and long-distance pressurized commute options via double Stewart platforms and tunnels, increasing mobility efficiency across the habitat. Our adapter's utility ports transmit power, regulate pressure, and allow data transfer between modules. Retractable covers and hatches provide dust protection and thermoregulation. A key advantage of our habitation paradigm is that each module and its connections can be represented as a node and its edges, allowing us to optimize our habitat layout using graph theory. Our habitat is made up of 2 parts, a bipartite science section and a connected community section. Our habitat's layout's connected nature ensures module accessibility. The science section's bipartite nature ensures that there are no connections between high-risk laboratories, preventing a chain reaction of system failures from a single high-risk malfunction. The low-risk laboratories are similarly separated from one another, preventing cross-contamination between labs serving different purposes. An airlock junction connects the community section to low-risk laboratories. Not only does our graph theory approach ensure the safety and resilience of the first months of habitation, but it also is beneficial for habitat scaling. It allows Earth-based support crews to use graph theory to propose habitat expansions and reason about optimal layout and daily commute lengths using reachability and shortest path algorithms.
The power system proposed to generate energy for all aspects of the mission consists of 3 components: kilopower reactors, solar panels, and batteries. The fission surface power system units are inspired by the kilopower reactors under Stirling technology, also known as Krusty reactors developed by NASA, and will be used as a constant energy source for the settlement. The kilopower reactors are designed to follow a single converter to heat pipe architecture, which increases heat transfer efficiency and electrical power output for each converter. Another advantage of this design is that the modular system configuration actually allows each individual unit to be tested. Did you know that the Krusty reactors are also self-regulating, meaning they maintain constant temperature to accommodate all potential states of the power conversion system? If power demand rises, the power supplied will also rise so that the reactor can maintain its preferred temperature, or vice versa. The nuclear fission systems can even be scaled up to one-day power electric propulsion vehicles and the transport of heavy cargo to planets or other extraterrestrial locations further than Mars. Considering its many benefits, utilizing kilopower reactors is a monumental next step toward deep space exploration to Mars and beyond. The layout of the electric heat wires promotes an equal distribution of heat, therefore cold and hot spots within a room are prevented. The design is also out of sight for aesthetic and spacing purposes. Efficient planetary and interplanetary communication is vital to drive home, where our focus is to create a sustainable life on Mars and the transfer of new research and knowledge. The transmission period between Earth and Mars can take up a possible 44-minute communication round trip. To reduce the time allotted to the greatest extent, the Drive Home mission utilizes an optimal communication system to transmit laser signals that help secure data and transfer it at an extremely high speed. Compared to a traditional radio system, optical communication can transmit more data in a given unit with less power. More data means more discoveries. To achieve this, 3 pre-existing orbital relay satellites will be strategically placed 120 degrees apart, creating an optimal connection with a deep space network. This constellation eliminates conjunction as an issue because it allows for at least one satellite to be in line of sight with Earth at all times. Radio frequency communications can offer ground-to-ground transmission of information.
The next aspect of the mission is the food system. In the first phase of the mission, the journey to Mars, the astronauts will primarily rely on preserved food from Earth. Lyophilization, thermostabilization, and irradiation are 3 methods of food preservation currently used on missions to the ISS, and these methods can be further adapted for the flight to Mars. For Phase 2 of the mission, the crew's stay on Mars, a circular agricultural system will be implemented to provide astronauts with adequate fresh nutrition sources. A variety of plants including quinoa, turnips, and strawberries will be grown. The plants will be cultivated in a vertical tiered aeroponic system, which uses root misting irrigation to be water efficient. The plants are fertilized by misting water with dissolved compost from food waste and ash from incinerated organic solid waste. Inside the greenhouse, a complex network of light, temperature, and water sensors are used to regulate resource use. As part of the plant's natural cellular process, oxygen is emitted, which is captured through distillation for external use. In addition, plants emit ethylene gas, which speeds up the ripening process. To extend shelf life by slowing down ripening, the BioKez filter is used to break down ethylene into carbon dioxide and water. Once the plants produce yield, any excess food will be freeze-dried for future use. Also, the food waste from the greenhouse system will be composted and used for plant nutrition. Aside from the fresh food grown on Mars, astronauts need a source of meat for protein. Lab-grown meat solutions can be used for the ease of production. To implement this, animal stem cell lines will be preserved using cryogenic freezing and transported on the journey to Mars. Once the samples reach Mars, they will be thawed and grown with carbohydrates and amino acids for growth material. Overall, the use of preserved food, Mars-cultivated produce, and lab-grown meat provide astronauts with a palatable and nutritious diet focused on astronaut well-being.
There are plenty of opportunities for surface exploration on Mars. For geological research, the crew will go beyond the landing site to various regions to collect rock samples to be kept in a Class 10,000 lab. The samples will only come into contact with stainless steel tools, aluminum, and Teflon to prevent contamination, similar to how they are handled on Earth. As for biomedical research, the Drive Home crew will spend an unprecedented amount of time outside of Earth in gravity. They will regularly send health data back to scientists on Earth for analysis. The crew will also explore how Martian gravity affects the flow of intravenous medication and inhalable medication, such as albuterol in nebulizers. Studying impact on medical technology makes travel to Mars more accessible. Botanical research will be conducted based on the long-term yield and growth characteristics of Mars-grown produce. Camera monitoring can be used to determine the viability of farmings on Mars. For engineering research, the crew will study how convection is affected in Mars's gravity, as well as the impact of Mars's gravity on machinery and electronics. In the International Space Station, as pictured in the diagram below, a system of fans manually circulates the air to prevent carbon dioxide poisoning. The drive home habitat will establish a similar system, but research shall be done to develop alternate solutions. Previously, many plans included establishing separate sites for each new Martian mission. However, a single site allows surface mobility assets to be more concentrated, allowing for more efficient exploration. This design is also far more cost-effective. Furthermore, pressurized rovers, unlike unpressurized rovers, can better serve as tools in emergencies. They can also have a smaller design since the crew will not need bulky suits. Unpressurized rovers, however, have already been used in several missions, and since they aren't pressurized, they can be less costly. The triathlete has 6 limbs with wheels. The limbs can also lock to function as feet and traverse larger obstacles. The triathlete also addresses previous lunar roving challenges, such as improving wheel design to maintain flexibility and reduce forces of impact. Drive Home will use the Chariot, which addresses previous issues with the lunar roving vehicle. Its wheels can better resist the harsh lunar dust, and it will have 12 wheels to increase traction. Active chassis suspension will allow the astronauts to easily access the rover. The Chariot can recharge itself, function autonomously, and receive controls from astronauts in the vehicle, from the HAB, and from scientists on Earth, although there will be a time delay from scientists on Earth.
Most of the water the astronauts will use can be supplied using a highly efficient wastewater recycling system similar to that used on the International Space Station. However, the farm will require large quantities of water as well, and this will not be recyclable. Thus, we need a different way to get water. Fortunately, the solution lies just below the feet of our astronauts. Our landing zone in Chryse Planitia is at a latitude believed to contain sporadic water ice roughly 5 meters below the surface. This ice can be extracted using a Rodriguez well, where water shipped from the Earth is used to create superheated steam to melt ice underground. The new liquid water is either removed for use or recycled into the well to create more steam. This system will provide us with a surplus of water that will likely well exceed the amount the colony requires. The best option for obtaining oxygen is water electrolysis, using an electric current to separate the hydrogen and oxygen molecules, thereby allowing them both to be used independently. Water electrolysis also produces hydrogen as a byproduct which can be used as fuel. Oxygen is not the only problem, however. One of the main challenges with life support in space is not how much oxygen you have, it's how much CO2 you can remove. This would be done with disposable air filters, which would be replenished every 7 years alongside a new crew. These filters are small, cheap, and light, and therefore can be shipped in bulk.
Waste management. The waste management unit is an ECLIS system that is connected to the restrooms in our habitat. The unit is an incinerator that first removes urine through distillation, then reduces fecal matter to ash, creating safe, highly nitrogenous and phosphoric fertilizer for use in the greenhouse. Medical systems. Confronting life in an adverse and foreign atmosphere requires substantial planning to keep crews as healthy as possible. Health considerations for the crew include both physical and mental care, as well as preparedness for both planned and unplanned health impact. Planned health care includes activities such as exercise and checkup physicals, while unplanned care capabilities will be carefully deciphered through NASA lists of accepted medical conditions, or AMCLs. Physical health. Because the Martian atmosphere is still thinner than that of Earth, reduced pressure will exert less strain on the astronauts' muscles, causing slow muscular atrophy. While crew members will not have to exercise the 2.5 hours required in zero gravity, somewhere around 1.5 hours will be required to account for the 38% Martian gravity. Exercise can be derived both from daily crew work and from exercise equipment stored in the multi-purpose exercise module. To account for caloric intake, vitamin and mineral requirements, we have referred to the National Institutes of Health's Estimated Average Requirements Guide based on a 2,000 to 2,500 calorie diet. Diets may also be adapted to consider high-risk environment factors, such as decreased gravity or higher radiation. We've defined water requirements for the crew to be between 74 and 101 fluid ounces daily. Radiation shielding in or on each member's person may be worn and woven into the suits that they wear, such as with hydrogenated boron nitride nanotubes. But shielding may also be taken orally or injected as medicine to the extent of our pharmaceutical capabilities. Mental health. The 7-year deep space round-trip mission requires tools to combat the several mental stressors. Spacious personal living quarters will provide privacy, while group activities will help fight loneliness and promote team cohesion. Finally, the crew will help care for life in the greenhouse, gardening to boost crew well-being and to provide a touch of home.
The timeline for the mission is as follows. In 2030, an SLS Block 2 launches the initial cargo and supplies, such as the rovers, 3D printers, and equipment. 200 days later, the cargo arrives, and, after Mission Control remotely confirms its functionality, the 3D printers begin assembling the HAB. A little over a year later, the HAB is completed, and after Mission Control confirms it is online, the crew is launched aboard another SLS. In another 200 days, the crew arrives and begins assembling the equipment, such as the Rodriguez well. Approximately 7 years later, the original crew departs, and a new one is launched aboard a third SLS. In conclusion, Drive Home offers a comprehensive approach to exploring the Red Planet. By using a human-centric design, we ensure the well-being of our astronauts. By using pressurized rovers and a carefully picked landing site, we provide abundant opportunities for scientific research. By extensively using ISRU, we ensure that our colony can be almost self-sustaining from day one. And by using a modular habitation system, we ensure that the mission can be expanded seamlessly. Humanity has been fascinated with Mars ever since we noticed that bright red dot in the sky. Drive Home provides us with the tools we need to reach up to that red dot and push towards new horizons.
A highlight of the program has definitely been the amazing resources and mentorship offered to us during the program. And we've also incredibly enjoyed the opportunity to learn more about the future of Mars exploration. On the other hand, a challenge our team faced was getting acquainted with all the domain-specific terminology without industry expertise. We also had to learn how to consider different constraints and requirements and combine a lot of different ideas to make one cohesive, comprehensive mission.
We are incredibly grateful for all the mentorship provided by Professor Noakes, Mr. Fritchie, Ms. Miller, and Ms. Baggio, as well as the rest of the SEAS team. Thank you for the opportunity to participate in the SEAS internship program and for all the funding, mentorship, and resources offered to us.
So great job, Mars exploration team. I invite you to please turn on your cameras and your microphones. We have several questions that have been posed. The first question is, why use graph theory?
That's a great question. Thank you. The reason why we did that was because during our literature review, we found that many papers cited the need for qualitative habitat attributes like scalability, efficiency, and accessibility. So in basing our habitat layout in graph theory, I wanted to provide a quantitative anchor for measuring our progress towards these goals, because graph theory provides a framework with known solutions and techniques through which we can work towards these intangible qualities in a tractable way.
Thank you. How many other landing sites did you consider, and what are the main things that made you disqualify the others?
So we considered a couple of other landing sites, including Acidalia Planitia, Arabia Terra, and Hellas Planitia were some of the other contenders. The main reason those were disqualified isn't necessarily because they were bad locations. It's more like Chrysi Planitia just has a very unique combination of circumstances. It has flat, smooth terrain, it has ice, it has a combination of different scientific opportunities like volcanic outflow, river outflow. It's just kind of a unique location that none of the others can really quite match in terms of how interesting it is and how relatively easy it would be to operate there.
And do any of you hope to go to Mars, or do you prefer planning for others to go?
Can I answer that question?
Sure.
Alrighty, so that's a really great question. And personally, if I had the opportunity to, I would definitely 100%, without a doubt, go to Mars. And I feel like that's such a part of our human nature, is that we are genuinely curious about what is beyond the atmosphere of Earth, what is in space and beyond. And a quote that I love from the famous cartoon is, "To Infinity and Beyond" by Buzz Lightyear. And I truly stick by that because I want to explore and open doors to the unknown. So I would definitely choose to go to Mars if I had the opportunity to.
How did you choose the factors that astronauts would need to provide the astronauts more comfort?
I actually went based off of some of the things that astronauts have faced on the ISS, some of the main challenges they face, such as loneliness and isolation, just a whole realm of mental health factors. And then for specifically medical factors, I went based off of, so there is a list a few lists that NASA has made. They're called AMCLs, which are accepted medical condition lists. And they're basically lists of all the possible factors and all the possible conditions that astronauts could face while they're out in space, specifically deep space missions, and just how prevalent they are. And that's kind of how we came up with what our capabilities would be based on the probability of them occurring.
Well, great job. Congratulations to your team. And thank you for presenting today. Our next presentations are by interns in the air quality group. Students conducted intensive research into air quality with the Air Quality Initiative group, hosted by the Globe Mission Earth team and NASA's Langley Research Center. Data will be shared on Globe's visualization system, a cloud-based geographic information system, GIS, of citizen science data. Students chose research projects based on their particular interest within the science of air quality. And we thanks to their mentors and for their guidance and expertise. So please join me. We will have 3 presentations from the air quality group, followed by the questions and answers. And our first air quality group was analyzing factors affecting flight cancellation and delay rates.
Hi, I'm Daniel Zhang from Washington State, and just 3 weeks ago, I had plans to attend the National TSA Conference in Kentucky. Unfortunately, instead of a week-long trip across the continent, I took a day trip to my local airport, as my flight was canceled and there were no other options that could send me there in time. What's worse is that my flight was scheduled for just before midnight, so I had to wait at the airport until the very next morning when my parents woke up to bring me back home. So in my 6 hours stuck at the airport, I wondered, why was my flight canceled, and did it have anything to do with the wildfires in Canada? And so that brings me to my research project, Unraveling the Skies, where I analyzed the flight factors that affect flight cancellation and delay rates, with an emphasis on weather factors. So why is this issue important? Well, first of all, flight delays are costly, as it costs the airline $100 per minute of a delay. This is also a time-consuming issue, as the average delay takes 70 minutes long. And lastly, this issue is still growing, as in just the past 5 years, the delay rate has increased by 26%. So these are the factors that I will be analyzing today. I first wanted to gain a bird's eye view on flight cancellations and delays, so I analyzed these 3 non-weather factors. Then, as I mentioned at the beginning, I wanted to emphasize on weather factors, so I chose to analyze these 5 factors. I chose these 5 because they appeared most common in my literature review. So what did I do after my literature review? Well, first, I collected my data from 4 sources. These sources allowed me to collect data on both flights and weather. Then I combined these sources and then set the time frame to the first 4 months of 2023. I also decided to only focus on flights that originate from one airport, the Chicago O'Hare International Airport. This airport is the biggest airport in the Midwest, which means it's responsible for most of the connecting flights in the United States. Choosing one location also simplified the weather collecting process, as I only had to focus on one area rather than multiple. After that, I analyzed the data with Excel and visualized it with line, column, and pie charts. Then, to calculate the correlation between weather factors and cancellation and delay rates, I calculated for the Pearson's correlation coefficient, and after that, formulated next steps to further my research. So now on to my results. First, I looked at the airlines, and out of the 12 airlines that operate at the Chicago O'Hare Airport, Frontier had the highest delay rate, and Southwest had the highest cancellation rate. Next, I looked into flight distance, and as you can see from this chart, flight distance was not a huge factor in cancellation and delay percentages, as we can't see any trend. Lastly, I looked into the departure time, and as you can see, there's a pretty visible upwards trend as the day goes on. And this is also seen in my own observations, as my flight was just before midnight, when the delay and cancellation percentages were the highest. So now we move on to the weather factors, where I rank them from lowest correlation to highest correlation. The one with the lowest correlation is PM 2.5. As you can see, the peaks don't very relate with cancellations or delays. However, I saw this as due to my time frame, as I was only looking at January to April. So for PM 2.5 only, I also analyzed 12 days from June to July, that were affected by the Canadian wildfires, where I could see a much larger increase in PM 2.5. And from that, which you can see on this graph, the correlation values were much higher than they were in the previous. This shows that events like wildfires still have a huge impact on flight cancellation and delay percentages. Next is surface temperature. And similarly to what we saw in PM 2.5, the correlation values were still very low, and there were some peaks that were relevant, but most were not. Next is wind speed, and as you can see, I've also included wind direction on the right, and wind direction had no correlation at all, similarly to PM 2.5 in the first 4 months of 2023. However, in wind speed, especially with cancellation percentage, you can see that in the circle I've highlighted, there are peaks of wind speed that correlate with cancellation percentages, and you can see that in both the cancellation and delay percentage graphs, showing that wind speed does correlate somewhat to cancellation and delay percentages. Next up is visibility, and what's interesting to note here is visibility has a higher correlation with delay percentages than cancellation percentages, which is different from what we've seen in the past factors, as usually cancellation percentage correlation is higher than the delay percentage correlation. And at the top is precipitation, which had the highest correlation with cancellation percentages. And as you can see on the graph, there are numerous peaks of precipitation where there's also an increase in cancellation percentage. So this pie chart shows the total minutes delayed split by the reason for the delay. And as you can see, weather takes a very, very small piece of this pie. And when compared to the cancellations, weather took a much larger piece of the pie, which we saw in our data analysis, as weather factors were oftentimes more correlated with cancellation percentages than they were with delay percentages. So in conclusion, precipitation had the highest correlation with cancellations, while visibility had the highest correlation with delay rates. And overall, weather factors were more closely correlated with cancellation percentages than they were with delay percentages. So how would I further my research? Well, firstly, I would investigate other factors, such as air pressure or the type and model of the airplane. Second, I would widen my project scope to include beyond the one airport that I investigated in this one, and enlarging the time frame to go beyond just 4 months. And lastly, I would use what I learned from steps 1 and 2 to create a machine learning model that could predict cancellation percentages and delay percentages to predict what flights could be canceled and delayed, which would not only save money for the airline, but also save time for us flyers. It appears as though we have arrived at our destination. I welcome you to the air quality team here at SEAS. For your safety, please stay seated until we have completely stopped. Thank you for flying with us, and I hope you have a fantastic rest of your day.
Thank you. Our next team was analyzing the correlations between PM 2.5 levels and early childhood asthma in their presentation titled California Breathing.
Hi, my name is Nithya.
And my name is Tanvi.
Today, we will be presenting California Breathing, analyzing correlations between PM 2.5 levels and early childhood asthma via examination of emergency department visits and hospitalizations from 2016 to 2019.
Understanding asthma is crucial in order to effectively assess public health in the United States. Approximately 6.1 million children in the United States are affected by asthma, and prevalence of asthma is known to be higher in children than adults.
Our objective is to investigate potential correlations between annual PM 2.5 levels and frequency of emergency department visits and hospitalizations for ages 0 to 4 by county in California, utilizing statistical methods and geospatial modeling. We utilized ArcGIS and R in this study in order to execute this process.
Asthma causes inflammation to the airways, which prevents the body from carrying air to and from the lungs. Air pollution is a trigger of asthma worldwide, and although asthma is not curable, it may be controlled through lifestyle modifications. PM 2.5 is an aerosol with a diameter of 2.5 micrometers or less, and may be suspended in the air for long periods of time. Sources of this pollutant may be naturally occurring or anthropogenic. Additionally, studies have shown associations between PM 2.5 and adverse health effects, particularly in the early adolescent and elderly populations.
Epidemiological studies show that particulate matter is positively correlated with asthma incidence, number of hospitalizations, prolonged number of days spent in hospitals, and hospital costs. Additionally, a research study from Cartagena de Indias in Colombia determined that one of the main causes of childhood asthma could be related to the concentrated dispersion of particulate matter.
This was our procedure. We had 5 main steps. First, we reviewed scientific literature related to PM 2.5 and early childhood asthma. We summarized sources and analyzed where they pulled data from to find reliable sources as well. We had around 7 to 8 sources. We then defined our research objective to be addressed in the study. This was our main goal for the project. Then we obtained data on PM 2.5 levels and ED visits and hospitalizations from reliable sources. We then computed this and analyzed this. And during analysis, we brought together all the components of the previous procedures.
Using open source data, we were able to obtain information about 47 out of 58 counties in California. These were all represented in the study to obtain a larger sample size and minimize confounding variables, such as socioeconomic and geographic factors of each region, among many others.
The next 4 slides will be geospatial maps representing 4 categories of data over 2016 to 2019. This consists of PM 2.5 at the 90th percentile, PM 2.5 and its weighted mean, hospitalization, and emergency department visit data. As you can see, the size of the circle of data point is directly proportional to the size of the data in relation to the legend, meaning the bigger circles are those with higher amounts of that data. These maps emphasize a correlation between data in certain counties. In all of these maps, we can see areas where high data counts are concentrated, thus having bigger circles in one area. This is mostly the Central California region. This pattern is repeated throughout each graph, as you can see. In all of these, there is that main amount or main area where there is that concentration of big circles. However, there are outliers. Based on the outliers, we know that this is not an extremely strong correlation, but it does indicate an association between these data sets. These conclusions can be used to reinforce further findings.
Among the statistical comparisons between PM2.5 and hospitalizations, there was generally a very low correlation. However, there is an exception to 2018 with a slightly higher R value than the other years. Hospitalizations have many confounding variables, preventing a stronger correlation, as only the most severe of the asthma cases lead to hospitalization. Additionally, socioeconomic factors that prevent access to healthcare may also impact these trends across California. With emergency department visits, there was a low to moderate R value present, and among these we may observe that the 98th percentile yields higher R values compared to the weighted mean of each year. Generally, spikes in PM2.5 levels lead to triggers which may cause emergency department visits due to asthma, compared to observing general averages over the years. And although we have observed correlations between these variables, there are several limitations that must be noted in this study, such as lack of data access due to the Health Insurance Portability and Accountability Act. Additionally, further information such as that of individual patients or data by hospital and PM2.5 at a daily or monthly level would increase sampling size and allow for outlier removal, shifting correlations accordingly. Some of the best experiences we had at SEAS were networking with other students and mentors across the country, learning more about air quality, exploring our passions within research projects, such as ours about public health and PM2.5.
Our main challenges were time zone differences, and since we were working with students all over the country, we had to figure out what times worked for different people without having any problems. We also had trouble getting access to data as a result of many guidelines that are implemented.
After taking AP Statistics this past year, this program really allowed me to connect what I learned in class to real-life applications. I also want to continue to pursue science and engineering in the future following the completion of SEAS.
This program heavily influenced my ability to do authentic research from the ground up. I gained skills in research writing, data modeling, and data analysis. It reinforced STEM skills I learned previously and reinforced my want to do STEM in my future academic and occupational career. Thank you for listening to our presentation. We would like to take some time to acknowledge all of our mentors who are pivotal in guiding us throughout our research process.
Terrific. Our next presentation is determining the correlation between economic factors and air quality, a study of the Las Vegas Valley.
Hello, my name is Sean Evan Gutierrez. I'm a rising senior from Las Vegas, and I go to Advanced Technologies Academy. I was part of this air quality team for the NASA STEM program, and my project is determining the correlation between economic factors and air quality, where I studied the Las Vegas Valley. For some background information, the Las Vegas Valley was ranked as the second worst metro in terms of population in 2018, and there's no signs of it getting better. Additionally, Nevada is the fourth most unequal state in terms of income. On the left graph, you can see that the top 10% in Nevada own majority of the wealth compared to the remaining 90%. This creates an issue of wealth inequality, where people living in less wealthy areas are more prone to producers of lower air quality, such as airports and factories, which inspired my project. So for my research question, I wanted to find out the correlation between median household income and PM2.5 levels in the Las Vegas Valley, which are the respective factors of economic and air quality. I believed through my hypothesis that PM2.5 levels would be higher for zip codes with lower median household incomes, and vice versa. So basically, for areas that are less wealthy, the air quality will be worse. And so for my data, I found my air quality data in terms of PM 2.5 levels through Purple Air and AirNow. And my economic data came from ArcGIS, where I found the median household income for each zip code. So for my method, I collected the air quality and economic data. I processed the data using Google Sheets, created various graphs and scatter plots, developed interactive maps, and then I calculated the correlation using the Google Sheets predetermined formula. And so for the Purple Air PM 2.5 data, on the left map, we could see all the different sensors in Las Vegas. Due to the nature of where the sensors are located, some zip codes are far away from sensors compared to other zip codes, so I had to assign each zip code to its nearest sensor. And so for the download tool, here are some of the processes that I use, such as downloading the information and making sure that that information was accurate. For the economic data, I also used income by zip code, which tracked median household income using census information. We can see here that towards the northern and eastern parts of Las Vegas, there's already a disparity in terms of sensors because even you can see as it's lower income here, there's not as many sensors in this area, which was a big problem for me. And so I used ArcGIS to develop an interactive map of the Las Vegas Valley. So orange represented lower income, which kind of mapped onto this map, which I used from applied analysis. And then the green represented the middle class, while blue represented higher class status. And while these numbers represent her air now sensors in terms of air quality. And so here's where some I collected the data. And so for each row, I had the zip code, the nearest sensor to it, the median household income, and the PM 2.5 levels. And I did this for each zip code in the Las Vegas Valley. And so for my scatter plot, I only got an R value of 0.103, which means there is little to no correlation between median household income and PM 2.5 based on the data that I collected and processed. So for my analysis, although it resulted in a significantly low R value, the reason for this may be due to the lack of data in certain zip codes. I pointed out earlier that parts of Las Vegas didn't have as many sensors compared to others. Additionally, I tested this over 1 year, where I averaged the data. If I tested it over multiple years, I may have gotten a different result that would have led to a more positive correlation, or a stronger correlation. Future steps to advance this project to its utmost potential include analyzing other economic factors such as poverty rate and proximity to certain structures that cause poor air quality. For my project, there's a wide variety of confounding variables that make it hard to make real conclusions, which I would like to examine further in the future. So, from the results of the study, there appears to be little to no correlation between median household income and PM 2.5 levels. This would indicate that lower income areas are not susceptible to poor air quality, which is a good thing, but further analysis and testing may be required to confirm this conclusion. Here are my sources. So thank you for the SEES program for allowing me to have the opportunity to delve into the real world of research. I'd like to thank all my mentors, Yitong, Dr. C, Sarah, and Farouk for their guidance and utmost support for helping me throughout this whole process. I couldn't have done it without them. Additionally, the SEES program was an absolute gift for me. I was able to connect with other like-minded students from across the nation and learn more about the world around me. For my air quality team, I didn't really pay attention to air quality prior to this program, but now I will be able to look more into it and see on a day-to-day basis how air quality will affect me and my future. As for the challenges for this program, the data collection process and analysis for me was pretty difficult as I wasn't able to collect the data that I wanted. For example, the lack of sensors, lack of zip codes. There was a lot of confounding variables that made my project hard, but my mentors guided me and helped me through the process to make it as simple and as effective as possible. On my personal reflection of the SEES program, I realized that when I go into my future career and have my future education, I want to emphasize climate change as I want to go into an entrepreneurial venture. I want to grow a business that will focus on mitigating the effects of climate change, which I've learned through the SEES program. Additionally, I talked about daily air quality and making sure that it's safe to go outside for me wherever I'm at. Additionally, in terms of my education, I've now been able to get some real firsthand research, and I would like to pursue that in the future as I want to grow and learn more about the world around me. So thank you so much to the SEAS program. Thank you so much for viewing my presentation. Have a great day. Thank you.
Terrific. We'd like all three teams to please turn on your cameras and your microphones. We have a question for team one. Are there any specific changes you'd like to see with regards to flight scheduling, considering the data on precipitation and visibility?
Yeah, I think we can make many changes now that we know how weather affects flight cancellation and delays. And I think one of them is first just making flyers more aware that, hey, this day there might be a higher chance that your flight is canceled or delayed. And second, I think we could also reschedule flights a lot earlier than like right before a flight is about to fly. So we could, a couple days or weeks in advance, we could schedule a flight to be hours apart or 1 hour or 2 hours away from the original time so that we could avoid high precipitation or low visibility times.
Great. Team number two, are there air quality factors other than PM 2.5 that could have affected your R values?
Yes, there definitely are other factors because there are other pollutants in the air. This can consist of PM10, urban pollution factors, man-made synthetic factors, but we chose to do PM 2.5 as there was more data availability. And since PM10, and compared to PM10, PM 2.5 is a smaller particle, so it's more likely to infiltrate the bloodstream, thus having a stronger effect on asthma. So although there are other factors, in relation to asthma, the smaller particle PM 2.5 is more likely.
And do you have personal experience or do you know someone with asthma that made you have an interest in this research topic?
So both of us are really interested in public health and healthcare in general. And in addition to that, I did spend part of life growing up in an urban city in India where pollution is pretty bad and did have effects on my health. So we just wanted to explore factors that might relate to that in the United States.
Great. And Sean, is there a charge for purple sensors? I'm wondering if that has a correlation based on the population and the number of sensors in the area.
Yes, I believe there is like it ranges in price in terms of the sensors, so not everyone has access to them.
Perfect. Well, thank you all for your outstanding research, and we appreciate your presentations today. We will continue with team presentations from the Air Quality Initiative Group, the Globe Mission Earth. Our next presentation is Where the Waves Meet the Sky, evaluating disparities in air quality between coastal and inland regions and the aftermath of Canada's wildfire outbreak.
Hi, my name is Kendall Cook.
Hi, my name is Shreya Sanjay.
And this is Where the Waves Meet the Sky.
Evaluating disparities in air quality between coastal and inland regions and the aftermath of Canada's wildfire outbreak.
Our research questions are: how does the air quality near the coast differ from the air quality inland? And how do past trends compare to the recent effects of the wildfires in Canada? The objectives for this project were to examine the difference in air qualities between two regions depending on their respective location. We also studied the impact of wind direction, wind speed, and PM 2.5 had on air quality in addition to the path of Canada's wildfire spread. Lastly, we compared the effects Canada's wildfire had on inland and coastal regions.
For our study areas, we chose Long Island and Albany. Long Island, as you can see on the map, is bordering the ocean and is a coastal region, and Albany is landlocked and is the mainland region for this project. So why are we studying the effect of the recent wildfires? Originating in northern Canada, the wildfires spread to the United States and had the largest effect in New York from June 4th through June 10th, which we will be calling the Wildfire Week. The picture on the right shows the air quality index in New York, which was unproportionately high, and I took the picture on the left, which is of the sky during this time. Both of these images show the magnitude of the impact of the wildfires.
These are the sources where we got our data.
Sky color is one of the qualitative factors, and it is the first factor that we're studying. And it can aid in comparing air qualities. The lighter colors in this map represent a milky sky or worse air quality, whereas the darker colors represent a blue sky or better air quality. At the start of this process, we looked at how sky color in coastal regions compared to inland for the entirety of the United States. In the northeast area, highlighted by the red circle, we can see that there's a greater frequency of sites that have reported a milky sky inland compared to along the coast. This sparked our interest and led us to explore the same phenomenon in our study area. This map was created using data from March through May of 2023, which preceded the wildfire week, and it is the time span for the standard trend for this and the rest of our factors. In this map, we see the same thing, with a greater number of sites reporting milky skies near Albany and inland compared to along the coast. Particulate matter 2.5 is the next factor, and is one of the more dangerous effects of bad air quality, and high concentrations of it is an important indicator of poor air quality. During the standard trend time span, Albany, which is in red, had higher concentrations of PM 2.5 compared to Long Island, which is in blue, signifying worse air quality in Albany.
The graph on the right shows the PM 2.5 measurements during the wildfire week. And during the wildfire week, Long Island's PM 2.5 measurement, according to Purple Air, was nearly twice as high as Albany's. Long Island reached a whopping 400 micrograms per cubic meter of air, whereas Albany's peaked at approximately 275. Nevertheless, many factors could have led to this wild event, such as wind direction and speed. And note that the y-axis scale for the standard trend is 0 to 40, while the scale for the wildfire trend is 0 to 400. This goes to show just how poor the air quality was in these areas during the week.
Wind speed is the next factor that we use to compare air quality. The standard trend graph on the left shows that on average, Albany had a lower wind speed, which is shown in blue, meaning that the pollutants in the air are less dispersed and the air quality is worse over the region.
The graph on the right shows the wind speed for the wildfire week, and it shows the hourly wind speed from June 4th to June 10th. Compared to the standard trend, the wind speed during the wildfire week was much weaker, contributing to a slower dispersion of particulate matter, and Long Island doesn't maintain a better air quality in this week. The charts shown represent the mean wind direction for June 6th, 7th, and 8th. These 3 days were impactful because they were the worst days during the wildfire week. The chart on the left displays the most recurring wind direction for Albany being west. The chart on the right shows the most frequent wind direction for Long Island being northwest. To better visualize, this map exhibits the course the wind traveled throughout June 6th through June 8th.
This map shows wind direction data collected over the course of the 2 months of our standard trend, and the majority of the arrows are pointing northwest or in the direction of Albany, meaning that the pollutants in the air are traveling from New York City and Long Island to the inland areas. This factor can also explain why Albany could have a worse air quality over this time, as the wind is carrying more of the pollutants towards it.
To answer the research questions, we can conclude that the air quality near the coast is better than the air quality inland, based on the factors observed. Moreover, this trend operated conversely during the wildfire week. Additionally, we found that wind direction had a substantial impact on the spread of wildfires and can explain why Long Island's air quality was more greatly hindered during the wildfire week. After this project, we recognized that being situated near a large body of water will result in a better air quality, and a rise in the atmospheric CO2 could cause the large bodies of water to begin to evaporate, meaning that populations located on the coast could lose this benefit in air quality. This is why it is important to preserve our bodies of water, as it also preserves the quality of the air we breathe.
Our future steps, if time permits, include looking deeper onto why Long Island was more profoundly impacted by the wildfires, and what other factors cause coastal regions to have better air quality than inland regions. Additionally, we plan to expand this research by adding more coastal and inland cities to make a more versatile closure to our questions. Lastly, we could continue our research on how to mitigate the effects of global warming and reducing the CO2 emissions rate.
We would like to acknowledge our Air Quality Initiative mentors as well as the SEA's Intern program.
Thank you. Our next team researched the variations in air quality between urban and suburban areas within New York City.
Hi, my name is Morgan Lynn, and I go to St. Vincent Ferrer High School in New York.
And I'm Toby Second. I go to Roosevelt High School in San Antonio, Texas.
And today we are presenting variations in air quality within New York City.
We'll be looking at differences in air quality within the urban and suburban areas of the New York Metro.
Before we get into our data, let's look at our air quality background. Air quality is a diverse field of science studying polluted and unpolluted air and its impacts on human health. For our study, we looked at particulate matter at the 2.5 micron level from purple air, visibility at the ground level, and wind speed and direction.
So our research question was, how does air quality of urban areas differ from the air quality of suburban areas in the New York Metro? And what factors could contribute to those differences in air quality in the New York Metro?
And for our methodology, we looked at our background research, then we formulated our hypothesis and research plan. We found suitable purple air sensors in NOAA stations for data collection, compiled purple air PM 2.5 data and local climatological data from NOAA, and we finally generated graphs using Google Sheets and Igor Pro for data analysis.
So our hypothesis was based off a 2008 CDC study comparing urban metropolitan counties to surrounding suburban counties, and they found that air quality in the suburban counties was shown to be better than the urban counties. A 2020 study in China found similar results in the multiple cities. So with this, we hypothesized that the urban areas of the New York Metro experienced greater levels of 2.5, in addition to poor visibility compared to the suburban areas.
And here is a map configured by ArcGIS of the purple air sensors we used. The urban areas we looked at were the Metropolitan Correctional Center, New York Metropolitan Transit, and Central Park. So they're really close proximity to each other. For our suburban areas, we looked at Newark Liberty International Airport, Westchester, and Farmingdale. So let's look at our urban areas. For the data we collected, we compared Central Park versus Metropolitan Center and Transit. And what we found was that there were similar peaks during wildfire week, which was from June 6th to June 11th, when New York was most directly impacted by the Canadian wildfires. So we see that New York Metropolitan Transit had the greatest peak.
We see this in the NOAA visibility data, that the peaks were found to be during the wildfire week and towards the end of the month. We found that Central Park peaked more frequently and before all the other urban areas, possibly due to Central Park being a very busy part of New York in the Manhattan area.
Now let's look at our suburban areas. For Newark, we see a strong correspondence between the visibility data and the PM 2.5 data. As we can see, we see a similar peak to the urban areas during wildfire week, and this corresponds to our NOAA data, where we see really low visibility. So this goes for the same in Westchester and Farmingdale. Now we can compare Farmingdale versus Newark and Westchester, and Newark Liberty International Airport has the greatest peak during wildfire week, showing greatest PM 2.5 concentration, which means it had the lowest air quality during this time. And now let's draw some comparisons. So when we compare our data gathered from our urban areas versus our suburban areas are labeled in red, urban areas are labeled in blue. This kind of goes against our hypothesis. We believe that our urban areas would have worse air quality compared to our suburban areas because it's more industrialized and busy. But we found out that our suburban areas actually have a greater peak during wildfire week and greater peaks throughout the month of June. And this corresponds to our visibility data. So suburban areas generally show lower visibility than urban areas.
The prevailing wind direction was northwest for the week of the wildfire week, so the wind could explain why New York had higher PM 2.5 concentrations compared to other suburbs, and why Farmingdale had the least.
For our analysis, we can see again that on June 7th to 8th, there's a significant increase in PM2.5 levels in both urban and suburban areas. And this is emphasized on our various peak dates, June 1st to 6th, June 7th to 8th, June 18th, and June 26th, and so on.
No visibility data corresponds with this. On all those days, we saw very significant spikes in poor visibility, meaning that the Canadian wildfires generally had a very drastic effect on bad air quality in the whole New York metro area. Wind direction also could have played a role in spreading pollutants from the urban areas to surrounding suburbs, and smaller spikes in poor visibility prior to the wildfires and after the wildfires could be from other sources like industrial plants, car emissions, and possibly construction due to New York being very busy city.
For our conclusions and further expansion, we looked at an article, and basically what we gathered from this article was that a lot of the greater PM2.5 concentrations in our suburban areas can be attributed to the greater amount of factories, plant vehicles, and other machinery that is causing wind to pick up more emissions from these factories and plants, as stated in this article.
Further research using a larger time scale, longer than a month, that we used, as well as looking to more surrounding suburbs, could provide more information about this phenomenon. In addition, studies into other large cities around the world, such as Paris, London, Beijing, could be used to draw conclusions about air quality in other large metros.
Here is our literature review and citations and other sources for data collection, and we would like to thank all of our mentors and NASA STEMs.
Terrific. Our next presentation is a geospatial approach to wildfire risk modeling using machine learning and remote sensing data.
Hi, everyone. This is our project Ember, a geospatial approach to wildfire risk modeling using machine learning and remote sensing data. My name is Hudson. I'm from Westview High School in San Diego, California.
And my name is Ria Gupta. I'm from Northwood High School located in Irvine, California. Introducing our problem. Wildfires are a problem that has occurred throughout the world, with more than 7.2 million acres alone being burned in the US annually. Connecting this back to air quality, smoke released from wildfires creates particulate matter that can cause an increase in the prevalence of respiratory diseases. And especially with the Canada wildfire, which is a rare event that put more than 50 million people under air quality alerts, really showed the world what it looks like to experience such a large wildfire event. However, these kind of wildfire events are a yearly occurrence for many Californians, and which is why we really wanted to solve this problem. But currently, what does wildfire management look like? Many wildfire institutions predict wildfire using vegetation indices, weather forecasting, and other biogeophysical factors. However, these factors are currently not enough, as more than 90% of wildfires are started by human activity. As such, it is important to understand the impact of human use of land cover and other factors as well. Wildfire presence. Here's a picture that I took of a wildfire, and you can kind of see how it correlates with PM 2.5 values in that area for that year. This is from the Silverado wildfire. So introducing their solution, we wanted to create a machine learning model that could provide real-time wildfire risk maps of the US. Our model currently covers San Bernardino County, California. We chose this area because it includes both a high risk of wildfires, as shown here, and low risk, to help us really test our model in both scenarios. Our training process included 5 input layers with 1 output layer to train our model as to what an ideal result would look like. So our first one is the land fire mean return, which shows average fire return in an area. Precipitation, which shows annual rainfall. Our Sentinel-2, which is from the ESA's Sentinel-2 satellites, to kind of show what land formations are in the area. Land cover, which shows how humans are using the land, for example, vegetation, agriculture, and residential areas. Moisture deficit and surplus, which shows areas of high moisture and areas of high drought, which will be correlated with a wildfire risk. And lastly, our output, which is provided by the USDA Forest Service, shows once again what an ideal result would look like.
So now that we have our 5 input layers and our 1 output layer, the next step was annotating our data set. So we did that by drawing several different polygons for each type of wildfire risk, as you can see in the top left image. And this is essentially teaching our model how it needs to interpret the information and what to look for. For our model architecture, we actually implemented 3 separate models. The first of which was the UNet. The second is the DeepLab v3, and the third is the pyramid scene parsing network. The basic concept behind these machine learning networks is that you have an input image, which is converted from raw pixels into numbers. And then you have what's called a convolution, which is essentially a sliding window that goes over patches of pixels in your input imagery to extract the most important features. And that's all learned. And then finally, you have a neural network that's placed at the end of these convolutional layers to search through these different features and determine what's what in the final classification. So here are a couple of images of the different model architectures. The first is the UNet. It's a symmetric model with both an encoder and decoder side, along with skip connections to connect both sides and retain information. On the right is a picture of the DeepLab v3 model architecture. And the most important thing about this is that it has something called an Atrius spatial pyramid pooling module, which essentially, instead of just being one sliding window, it actually has several sliding windows at different fields of view, which gives the model a better idea of what it's looking at. And then the pyramid scene parsing network, likewise, instead of different fields of view, has different scales to, again, give the model a better context as to what to look for.
So these were our results. These results allowed us to analyze our performance over actual machine learning models. So our F1 score is a combined mean of both precision and recall. This measure indicates our model's performance across a single metric. And so as you can see, our UNet model performed the highest with 87.61%. As for recall and precision, recall indicates the proportion of true positives that were correctly identified by each machine learning model. Precision is the proportion of true positives that were predicted for each class. For example, high risk, low risk, medium risk, etc. UNet had the highest precision, while the pyramid scene parsing network had the highest recall.
And these are our results graphs. So for each epoch, we actually calculated several different metrics, the first of which was accuracy. Final accuracy for the UNet was 80.9%, for the DeepLab v3, 76.7%, and PSPNet, 75.1%. And then additionally, we also calculated the validation loss. The final validation loss was 0.53 for UNet, 0.58 for the DeepLab v3, and 0.63 for the PSPNet.
Going into analysis and conclusion. Analysis based on our F1 and recall and precision scores, our models can realistically be deployed and used for various reasons by the general public and fire departments across California. Our next steps would be to increase our study area to include the rest of California and hopefully eventually the rest of the United States. How would we apply this model? Across the world, many communities don't have access to real-time wildfire risk maps that are both accurate, efficient, and accessible to them. As such, we would like to be the first in giving such an accurate model, and especially we want to help low-income communities that may experience several barriers that prevents them from understanding wildfire risk in their area, and which prevents them from ultimately preparing for a wildfire event. Thank you. We want to thank all of our mentors that made this internship possible. We really could not have done this without you. We would like to thank all the organizations, the NASA SEAS program, UTA, Toledo, which you guys have been so amazing, and we're really thankful. Going into our personal reflections, both Hudson and I really love working on this internship. It has been so nice to meet such great people, and we're really looking forward to taking this knowledge with us in the future. Thank you so much for listening.
Great. So we would like all the air quality teams that just presented to please turn on their cameras and their microphones. And we have a question for Team 4. The question is, how can your research be applied to help various communities?
I can take, if that's okay with you. So because we found that the coastal region had a better air quality compared to the inland region, I guess we can pay more attention to the inland regions that we found during our research did not have a frequency of air sensors or tools to better the air quality by potentially building more tools in these areas or implementing regulations to better the air quality.
And then for team number 5, how did you choose the locations to collect data?
Yeah, I could take that question. So for our urban areas, we chose heavily populated areas with close proximity to a number of sensors for data collection. And for our suburban areas, we wanted to take a closer look at densely populated, like well-known suburban areas in the New York Metro, and specifically look at airports like the Newark Airport, which showed us the lowest visibility out of all the suburban areas.
And a question for team number 6. Do you think the movement restrictions and reduced industrial activities from COVID-19 pandemic have any effect in your air quality data and model?
Yeah, so I can take that question. So one of our input layers for our machine learning model was land cover. And since our data for this model was used from 2020, we believe that industrial activity slowing down and obviously the COVID pandemic impacted how land was used during that year, which had an impact on what wildfire risk outputs we received as a result in all 3 models.
And also a question for team number 6. How are you planning to continue the research you've done for the Air Quality Initiative?
Yeah, I can take this question. So in terms of continuing on our research, we're planning on presenting at the American Geophysical Union conference, as well as potentially publishing our paper. And we'd also like to expand our research into including potentially more data sets on different types of models, and also different types of data, such as like LiDAR data or synthetic aperture radar data, which could potentially improve our model and make it more accurate.
Great job, and congratulations to the air quality teams. Interns in the Astronomy Open Cluster project determined the age and distance to an open cluster of stars. Students used astronomy software to analyze the data collected and calculate the member stars' magnitudes. Our thanks to their project mentor, Olivia Cooper, for her leadership and commitment to this astronomy team. Please join me in welcoming the Astronomy Open Cluster team.
Hello, this is the age and distance of an open cluster team. My name is Luna Sudani, and my teammates are Mohammed, Maureen, Juan, Oren, and Yuri. And then our team mentor is Miss Olivia Cooper.
We start off with an introduction to what open clusters are. Open clusters are loosely bound groups containing anywhere from tens to hundreds of stars. These structures are not stable and they will eventually disperse, meaning that open clusters are mostly found in spiral or irregular galaxies because these are the galaxies in which stars are still forming, as opposed to being found in elliptical galaxies, galaxies in which star formation no longer occurs. Open clusters are typically younger than globular clusters, and within our own Milky Way, there are around 150 known open clusters. As for how open clusters are formed, all the stars in a given open cluster are formed by the same molecular cloud or nebula. Gravity groups the dust together, and this cloud collapses once a minimum submass is reached, eventually forming a star as seen in B on the image to the right. Eventually, the amount of stars in an open cluster ranges anywhere from 10 to 10,000 stars. Stars eventually do disperse from the open cluster after a few 100 million years.
Composition of an open cluster. The majority of open clusters disperse prior to the majority of stars reaching the end of their life cycle, resulting in a prevalence of young stars with most clusters. Additionally, young open clusters are characterized by a higher abundance of blue stars, whereas older clusters predominantly host yellow stars. Lastly, open clusters are less densely populated in comparison to globular clusters. Where can they be found? Open clusters within the Milky Way are typically found in a dense region of the galactic disk, where layers of stars, gas, and dust partially obstruct our view. Due to their location, these clusters are susceptible to being gradually disrupted by the gravitational influence of passing objects, explaining why most open clusters are relatively young, with ages less than 1 billion years. In contrast, older star clusters are situated further away from the galactic.
NGC 1245 is an open cluster first discovered by William Herschel in 1786. It's located in the Perseus constellation and is estimated to be over 27 light years across. There are officially 506 stars in NGC 1245, but we decided to exclude 15 of the cluster as they were too faint to perform photometry on. In order to efficiently analyze each star correctly, we used Shikharimi's numbering system from the paper La Masio Galactica. We sourced our data from the telescope located in the Roque de los Muchachos Observatory in the Canary Islands. This telescope belongs to SARA, an organization of universities including Florida Tech, Eastern Tennessee, and others. SARA allows smaller universities to have access to telescopes in order to further their astronomical departments while keeping costs manageable.
In order to properly analyze our data, we use photometry and filters. Photometry is a measurement of light as data to analyze and gain information. We used images taken by our telescope with filters that work by taking all but a certain range of wavelength, which changes with each filter. Images of the cluster were taken through the B or blue filter and the V or green filter, and they will be used to obtain the color index and spectral type of the star. We use a reference star to find the magnitude of the target star's and astro image J because its magnitude is known for each filter. Astro image J being the application we use to analyze our data. In order to find the age of NGC, we had to begin by analyzing the B and V filter calibrated telescope images using the multi-aperture photometry feature in Astro Image J. Most stars were found on the 1/22nd exposure images, while dimmer stars were found using the 90-second exposure images. The apparent B and V magnitudes of every other star were found in comparison to our reference star 125, as the magnitude of that star was already known. The B minus V was calculated to find the color index of each star, which will then be used for the spectral types.
However, we can't use the raw B and V counts from Astro Image J because of reddening. So interstellar dust clouds absorb, scatter, and redden light. This is because red light has a longer wavelength than blue light and is more difficult to scatter. That's why when you look outside, the sky is blue, because blue light travels in smaller waves and is thus easier to scatter. Most stars appear redder than their true color, so we have to correct for this reddening in our analysis. To do this, we got a value of 0.3 magnitudes as our reddening value, and we subtracted that from the raw B minus V value to obtain what's called the true color index. Then we also corrected the apparent V magnitudes by subtracting 3.2 times 0.3, and then plotted that using our data. So using Python, we plotted the corrected V values on the y-axis and the true color index on the x-axis. And then we overlaid a ZAMS line, or the zero-age main sequence line, over it. So we kind of created a color magnitude diagram, which is the observational version of the Hertzsprung-Russell diagram, which is pictured here, which shows the different life cycles of stars given their luminosity and surface temperature. So to estimate the age, we found the part of the graph where most stars are turning off relative to the ZAMS line. So for our cluster, the cutoff star was star 141. And we calculated the spectral class of each star, so O, B, A, F, G, K, or M, using the color indexes. And we found that our star 141 was class A, which put NGC 1245 at approximately 1 billion years old. So this is the table we refer to ensure that to get the spectral type of each star. And then we generated this bar graph using Python, which shows the spectral types. And as you can see, the most stars are in class A, which are hot young blue stars, which coincides with what Juan was talking about with the composition of a stellar cluster.
By plotting the corrected V value, representing the magnitude on the y-axis, and the corrected B minus V value, representing the color index on the x-axis, we're able to create a color magnitude diagram. Then, by overlaying a zero-age main sequence line, we are able to determine the turn-off point, or turn-off star, which represents the point at which the cluster, or the stars in the cluster, begin to turn off of the main sequence. Then we can use the turn-off star to determine the age of the cluster.
In order to determine the distance to our star cluster, we have to use the distance modulus equation, which details as 10 to the power of the star's apparent magnitude minus the star's absolute magnitude plus 5/5. However, the star's absolute magnitude of any star in NGC 1245 is not known, which is why we have to use a standard star whose absolute magnitude is known, but is similar in spectral class to one of the stars in NGC 1245. For that, we used Eta Cassiopeae, whose color index is around 0.66 and absolute value is 4.59. And we used star 113 from NGC 1245, whose color index was 0.663 and apparent magnitude was 16.352. Both stars were of the G spectral class. In the end, we found that the distance to NGC 1245 was 2,251 parsecs, or 7,338 light years away.
So why do we study open clusters? Open clusters contain many young stars, which provides insight into the star's life cycle and formation. By recording the apparent brightness of stars in open clusters and comparing them to known amounts of light emitted, which is known as the absolute magnitude of other stars, we are able to determine the distance to the cluster. Open clusters also allow us to understand stellar dynamics and populations, and uniformity within clusters and young age of stars aid in exoplanet detection and characterization.
Their strongest points were teamwork and coordination. There was no confusion about tasks, and we all did our parts diligently. In addition, we managed to use Python to automate some of the visuals, which was an impressive task. Our weakest points were the fact that we had to manually perform photometry. This not only left slight inconsistencies and room for error, but also made the project much more arduous and time-consuming. Another difficult element was the time zone difference. As some of us live on the East Coast and others live on the West Coast, it was difficult to find meeting times that worked for all of us. This internship not only allowed me to network and collaborate with my highly motivated peers, but also piqued and cultivated my interest for research in space.
I am very grateful for this internship as it allowed me to do authentic research, which is something that I wouldn't have otherwise experienced. I also gained valuable experience in collaboration as well as collecting and processing data, which will be useful skills to have in my future career.
I'm very grateful for SEAS in this internship as it has given me the opportunity to conduct research and experience teamwork within that research alongside peers who share my interest within the subject. I much better understand the importance of flexibility when conducting research, and I look forward to continuing to do so for many, many years to come.
I'm grateful for SEAS because it exposed me to authentic astronomy research and it gave me the opportunity to network with people who share my same interests.
I truly appreciate the opportunity to be a part of the SEAS internship and the chance to participate in hands-on research in astronomy. This program has solidified my interest in the scientific research in space, and I'm excited to take what I've learned from this program to pursue my interest in astronomy further in the future.
I'm grateful for the SEAS internship as it allowed me to do research with a topic that I've been interested in while working alongside hardworking peers and helping me realize it is something I want to do more of in the future.
We would also like to give a special thanks to Mrs. Cooper for guiding us throughout this internship and Professor Tom Rutherford for providing valuable telescope data.
So congratulations, team. We would like all of the members of the Open Cluster Astronomy team to please turn on their cameras and their microphones. We have several questions for your group. What was your experience in astronomy prior to coming to SEAS?
So for me, I didn't have that much experience doing astronomy research. I mostly just read about astronomy through things like the NASA website and YouTube videos. And SEAS was the first opportunity I had to actually dig in and do some real research.
Great. What challenges did you encounter as a team while working on your research project?
As we mentioned, As we mentioned, we kind of struggled with doing manual photometry as it left slight inconsistencies in our magnitudes and such. And we had to use those magnitudes throughout each part in our project. And so we kind of had to go back and forth throughout the entire project and fix any details we might have gotten wrong.
Great. Did you learn anything surprising while doing your research?
I can take this. So we didn't learn anything particularly surprising, as this has been already, the agent distance to this particular cluster has already been calculated. So we were really looking for our results to be similar to what's already known. And that is what we got. We got pretty similar results, and we are satisfied with our outcome.
So research validation is a critical and important piece. So congratulations to your team. You did an excellent job. We will be taking a 20-minute break. We invite you to watch highlights of student accomplishments during the Earth and Space Science course. A special thanks to Teresa Howard and Asha Carmacher for scoring and preparing these highlights. We will continue with student presentations at 3:35 Central Time.
For more than 50 years, NASA has been collecting and providing data on Earth's land, water, ice, and atmosphere. Now, a new era of Earth science has begun. Together with international partners, NASA will launch the SWAT mission to provide the first ever global survey of Earth's surface water, the oceans, lakes, and rivers that affect all of us. But we also need to understand our planet as a complex whole. That's why NASA will launch a fleet of state-of-the-art satellites forming the Earth System Observatory, which will create a comprehensive 4D view of Earth from bedrock to atmosphere like never before. The Earth System Observatory will arm us with crucial data to help us address climate change and protect our communities. But how do we get this critical information to the people who need it? Introducing the Earth Information Center. NASA, working with our federal partners, will equip decision makers with the information they need to mitigate, adapt, and respond to climate change. We will create a greenhouse gas monitoring system and make data about our changing planet accessible to those who need it most. New satellites observing in the sky, and an information center here on Earth, protecting our planet for the next generation.
Welcome back to the SEAS 2023 Science Symposium. Our next projects are from the Earth System Explorers virtual internship that engages interns with NASA satellite data products, as well as digital tools that scientists use to monitor and document our changing landscape and climate. This year, teams focused on land cover change and the public health threat of mosquito vector-borne disease. We are fortunate to have several mentors with their expertise and educators as mentors to this outstanding group of students. Our thanks to Dr. Rusty Lowe, Cassie Sofing, Andrew Clark, Petter Nelson, and Dr. Erica Podest as members for the Earth System Explorers Group. We will have several presentations, and we invite you to put questions for each of these teams into the Slido app. Please welcome our first team that is exploring the relationship between land cover classification and urban heat island intensity.
Hello. Our project is exploring the relationship between land cover classifications and the intensity of the urban heat island effect. All across the globe, there are areas in which dense urban centers are surrounded by rural landscapes. During the 1800s, scientists began to observe a positive temperature differential between urban centers and their rural counterparts. Scientists believed that despite their geographical proximity, urban areas became hotter as a result of human activity. This phenomenon is known as the urban heat island effect, which is the center of this project's research. The intensity of the urban heat island effect can be quantified using the average temperature difference between urban and rural areas. Although many factors may contribute to the urban heat island effect, our group aimed to compare the intensity of this phenomenon with land cover classifications in our areas of interest. Ultimately, we hope to answer the research question, what is the relationship between the disparity in land cover classifications, most green versus most urban, and the intensity of the urban heat island effect?
In order to solve our research question, we use land cover data from each group member's area of interest. Each AOI is a 3 by 3 kilometer space with 37 evenly spaced data points. We then use Landsat surface temperature data, or LST, to create heat maps that highlight the varying temperatures between the rural and urban area. From there, we calculated the intensity of the urban heat island effect in each of our AOIs, which is simply finding the difference between the average urban and rural temperature. We then classified each of our AOIs using Collect Earth Online and created graphs showing the distribution of land cover elements, which can then be analyzed. To create the images on the screen, we use the Google Earth Engine, a platform used for analyzing geospatial data. These images represent the heat maps in each of our AOIs, which were derived from Landsat land surface temperature data. Each image represents the aggregated LST data spanning from 2013 to 2022. We specifically selected the months of July and August for each year as they represent the peak summer season where the urban heat island effect is most prominent. To visualize the temperature distribution, we assigned a color palette to the images. The blue color represents lower temperatures, indicating cooler regions, while the red color represents higher temperatures, indicating warmer regions. Each image utilizes its own relative temperature scale, where the average real temperature serves as the minimum value and the average urban temperature serves as the maximum. The urban heat island intensity indicates how severe each urban heat island is, which can further be analyzed to the percentage of land cover elements in each area of interest.
In conjunction with the previous visualizations, these graphs were created using Python and show the percentage of tree cover or rural area in each AOI location we investigated. The data comes from Globe Observer AOIs that were ultimately classified in CEO. As shown, AOI 31 had the most tree cover and was therefore the most rural out of the three AOIs. AOI numbers 3 and 32 were similar to each other in percentage of land cover and were more urban compared to AOI 31. Using the percentages of tree cover from CEO, in each AOI we created these scatter plots to visualize our results. These plots compare the UHI intensity with the percentage of tree cover and urban land cover in each AOI. As shown in plots, AOI 31, which was the most rural and had the most tree cover, also had the lowest UHI intensity. In contrast, AOI 3 and AOI 32 were more urban and had a much higher UHI intensity at almost 9. Ultimately, with these graphs, we were able to answer our initial research question of how land cover classifications correlate with the UHI effect. As seen in the graphs, the more tree cover and rural an area is, according to our classification method, the lower the UHI intensity. On the other hand, the higher the urban area, the higher the UHI intensity.
Ultimately, due to the scope of the project, we only had the time to analyze a few AOI locations. As a future improvement, it would be beneficial to analyze as many AOI locations from Globe observers as possible to make concrete findings about this correlation. By beginning this research, we have reinforced the validity of land cover classifications, and we now have the capability to generally predict the UHI intensity of locations based on their classifications. Moving forward, it would help this research to either adopt a mathematical prediction model or create a comparison of the UHI intensity to other methods of classification. Lastly, we would like to thank the SEAS program and our team mentors for their help during our project and for giving us this incredible opportunity. SEAS Earth System Explorer mentors Dr. Rosanne Lowe, Ms. Cassie Sofing, Mr. Peter Nelson, Dr. Erica Podest, Andrew Clark, and James Irvin.
Please welcome the next team researching a forest analysis of remote sensing driven mosquito habitat prediction in West Africa.
Hi, I'm Neil, and I'm joined by my team, Ruchi, Ryan, Callista, and Andrew, to present our project, a random forest analysis of remote sensing-driven mosquito habitat prediction in West Africa. Mosquito vector-borne diseases such as dengue, West Nile virus, malaria, and more pose a significant global health risk to millions of people. Therefore, there is a need for intelligent and automated mosquito habitat prediction models to assess mosquito abundance. These forecasting models would enable healthcare and government authorities to better address areas of interest that may be at risk for mosquito vector-borne illnesses. Our work aims to answer this research question. How effective are random forest models at predicting mosquito habitats in Benin using remote sensing environmental data? Additionally, our research offers a novel approach to mosquito prediction by performing a time series analysis on exclusive remotely sensed globe data in a unique location, Benin, via multiple factors to accurately predict mosquito abundance.
By plotting the Globe Observer app's mosquito habitat mapper data in ArcGIS, we were drawn to Africa and found that the country Benin had a significant amount of data. The larger amount of globe data available in Benin demonstrates the impact of mosquito population on the community, contributing to our desire to study this area. Furthermore, Benin has relatively stable climate patterns and publicly accessible data we can use to predict mosquito habitat abundance. Historically, Africa has faced constant mosquito outbreaks, and our project would be impactful for forecasting future outbreaks and developing prevention strategies.
To approach our research question, we started with Globe mosquito habitat mapper data and 4 remote sensing environmental data sources at our target location. We isolated the years 2018 to 2022 and concatenated all the data sets. We filled null larvae count values with zeros and accounted for the imbalance of zeros through oversampling. We trained both a random forest regressor and a random forest classifier to predict mosquito larvae counts as numerical values or levels of abundance, and we hyperparameter tuned our model through random search optimization. Finally, we used evaluation metrics to evaluate the accuracy of our prediction models.
For our climate data, we use NDVI, humidity, rainfall, and temperature data. In order to merge all these datasets into one, we used the Globe MHM dataset as the base and matched appropriate measurements with the correct date and location. The rainfall and NDVI datasets we were merging had hundreds of observations on the same day, so we decided to average the values in order to accurately represent the day. Once all the datasets had one value per day or location, we began to assign them to the corresponding observation in the Globe MHM dataset.
After creating a combined dataset in order to train our model, we had to eliminate unnecessary data as well as account for data imbalance, which leads us into pre-processing. We first used the larvae count column to create a new column to classify larvae into 3 tiers. Then we dropped the data and location variables so our dataset only included our 4 environmental features and our 1 classifying feature. We split our data into a 90-10 train split, and since our data had an influx of zeros, we ensured a consistent test by using random state.
Here's what we found from training our model. The random forest classifier achieved its best accuracy at 85.12%, and looking at our confusion matrix, we can see that the data was overtrained with zeros and simply did not have enough data with the label of magnitude 1 or 2 to make the accurate decision. That's why our model favored predicting zeros, where rare instances which would actually guess a 1 and almost never guess a magnitude of 2. Random forest classifiers proved to be well suited for predicting mosquito habitats in Benin. While predicting the true mosquito larvae count also has its benefits, categorizing the larvae count into a tier system like ours holds real-world relevance to aid healthcare and government authorities in understanding the threat of mosquitoes in their area and making plans to address the future disease prevention. This study was limited by the availability and accuracy of the data we acquired, since Globe Observer Mosquito Habitat Mapper observations come from citizen scientists. It may be important to acknowledge the lack of accuracy or consistency in data collection between observations, for example, the use of manual versus automatic location mapping, or the types of tools available to volunteers, such as microscope lenses, may affect the accuracy of the observations and thus may be important features to consider in our classification model. In addition, due to the inconsistent nature of our data, the number of representative data points to use in our dataset was also very limited. And our model could definitely be improved by acquiring data with regular and consistent mosquito observations.
In conclusion, our project demonstrates the implementation of random forest machine learning models to predict mosquito larvae abundance in Benin. Our results provide valuable insights for future research to apply machine learning architectures to remote sensing data in other target areas, and to develop surveillance or alert systems to aid in mosquito-borne disease prevention efforts. Based on these results, future work could leverage additional features such as location and date, or integrate more mosquito datasets from other sources, such as iNaturalist or Mosquito Alert, to acquire more consistent data for improved prediction accuracy.
Many thanks to the NASA and peer mentors for their insight and support, and thank you to all the SEAS coordinators who worked to organize this program. We thank the audience for listening, and we are open to any questions you may have.
Great job. Please welcome the next team exploring the influence of tree density upon the spatial distribution of mosquito populations.
Hello, I'm Vivek Apipatla.
I'm Shayna Jumokamga.
I'm Izzy List.
And I'm Emmy Shockley. This is our presentation on the influence of tree density upon the spatial distribution of mosquito populations. This is a little overview of what we'll be going over today. This is the About slide. Mosquitoes pose an ongoing global threat to public health, and it is essential to determine the conditions for mosquitoes thrive. The aim of this project was to identify the effects of tree density on mosquito populations using Houston, Texas as a case study. Houston's subtropical climate and the city's large population of disease-carrying mosquitoes make Houston an ideal climate for mosquito breeding and the spread of vector-borne illness. From Houston's data, we can identify the relationship between tree density and tree concentration with mosquito populations to better see mosquito risk. We hypothesized that an increase in tree density will lead to an increase in mosquito populations.
The first tools we used for this project was the Globe Observer program, which focuses on building connections with people and their environments. Globe has 2 subdivisions that we used. The first was the Land Cover Observer tool, in which we were able to gather knowledge about the urbanization and land cover of Houston. The second tool we used was the Mosquito Mapper, which we used to get data about the spatial distribution of mosquitoes in the context of Houston. ArcGIS is another tool we used in combination with the mosquito mapper, as it helped us get a map of the mosquito in Houston. Finally, we used GitHub program to analyze the land cover photos and determine the tree density.
To start our research, we first selected 3 AOIs, or areas of interest, within the city of Houston, Texas. We then utilized Globe Observer, a citizen science application that collects observational data and images from users throughout the world. In this case, we gathered just over 500 photos of land cover data taken by Houston residents within the 3 areas of interest. We then uploaded these photos and Globe data to a GitHub program that analyzed these images and generated plots depicting the tree densities and distribution throughout our AOIs in the general Houston area. We then obtained an ArcGIS polygon layer of our areas of interest and layered it onto the mosquito population data from iNaturalist and Mosquito Habitat Mapper that were in the region. In doing so, we were able to determine if tree density was a factor in mosquito numbers by generating 3 figures of Houston, Texas, one depicting tree density, one depicting tree concentration and urbanization levels, and one depicting mosquito population levels.
The images presented above represent our quantified data of tree density shown in Figure A, land cover distribution shown in Figure B, and mosquito data population shown in Figure C.
As shown, we have 3 maps of Houston, each representing different things. Figure A and Figure B, the maps of tree density and urbanization, are inversely related, which makes sense because in places where there's more urbanization and buildings, there's less space for these trees to grow. Figure C, on the other hand, is very similar to Figure B, showing a direct correlation between mosquito abundance and urbanization, and an inverse relationship between mosquito abundance and tree density, which completely contradicts our hypothesis. The best possible explanation for this is that there's more people in the places that are urbanized, which means more disease vectors for these mosquitoes. And as stated before, in places that are urbanized, there are going to be less trees on average. Therefore, there are more mosquitoes in places with less trees. This doesn't mean that less trees automatically leads to less mosquitoes. It just means that more urbanization leads to more mosquitoes, and this urbanization also leads to less trees.
From this data, we can conclude that there's a positive correlation between urbanization and mosquitoes, and a negative correlation between tree density and mosquito numbers. In the future, this data could possibly be utilized in determining which locations and groups are at the highest risk for mosquito-borne illnesses. Places with high levels of urbanization are more likely to host more significant mosquito populations, and thus the citizens of these areas are at a higher risk. Going forward, we could expand this experiment by choosing different locations and more areas of interest to solidify our data by cross-referencing any new information with our current data to confirm our findings. Overall, this data refutes our hypothesis, in which we predicted that the higher the tree density, the higher the mosquito population.
On the behalf of our team, we would like to acknowledge the people who have made this program possible. Thank you to Dr. Roseanne Lowe, Ms. Cassie Solfing, Mr. Peter Nelson, Dr. Erica Podest, and Andrew Clark. And thank you for listening.
Please welcome the next team whose research is about the urbanization in rural towns, a case study of West Columbia, Texas.
Hi, my name is Cashton McCracken, and my project is over urbanization in rural towns, a case study of West Columbia, Texas. So the development and commercialization of rural areas has increased drastically over the past few decades. So my goal in this project was to analyze and describe the changes in urbanization that can be seen through satellite data and the testimony of rural residents. The world is constantly changing around us, and these regions we once knew to be empty are turning into populated areas. So I want to know, are the effects of urbanization in rural communities recognizable from land cover data? So just some background information. What is urbanization? Urbanization is land cover and land use change due to a specific cause defined by buildings, roads, and human development elements. So what am I studying? I'm studying the changes to the physical geography and visual changes in satellite imagery. It contributes to NASA's land cover and land use change program. I'm addressing observations and data from ground land cover photos, and I compare them with Landsat satellite imagery. So this comparison is characterizing the land cover change and the land use change in areas of study. So what is my area of study? It is going to be the small ranch home in West Columbia, Texas. So what was my methodology? I collected my data from a multitude of different places. Google Earth's time-lapse satellite images let me see from 1984 to 2022 in the same place. It would time-lapse the images, and I could watch as the landscapes would change around me. I would use NASA's Worldview Earth data to look at cloud changes over years. I used Landsat Time Series Explorer to look how flora was influenced by the different years. I could see when droughts happened or whenever abundance of rain happened. I also use Globe and Globe Observer for my land cover photos to identify photos that may help me understand even more about what the area is like. So all of the photographs and satellite images that I've gathered, I've compiled into timelines, and I've compared the differences that are visible in the timelines. As you can see, the river is beginning to smooth out rather than be so rigid around the edges. And this is where you can see the difference in flora. So satellite images work very well, but they're not always accurate. This is an image from 2023, but it is not true. The buildings that are in this image were bulldozed several months ago. So a way to counteract this lack in data would be to hear testimony from someone who's witnessed this change happen before their very eyes.
My name is Roseanne Smith. I grew up in West Columbia, Texas on a ranch located next to the Brazos River. The river flooded many times, and every time it flooded, you could see a difference in the banks due to the sloughing of the sand. From 1965 to 1973, while I lived in Houston, Texas, an extravagant multi-million-dollar community was developed right across the highway from the little ranch house I grew up in. Over 2,000 people now populate the community that was once swampland. After all the development in 2023, my childhood home was bulldozed. I have many memories with my sister in the front yard of our home, catching lightning bugs and watching the stars. The sky's not as bright as it once was because of the growth that West Columbia has seen. We had many pecan trees and oak trees. There was also moss in all the trees, and because of all the development, a lot of the trees and moss are gone.
So hearing these developments from this testimony, I want to further understand, when did these changes happen? When did the moss disappear? When did these communities pop up? So, in my conclusion, through analysis of satellite imagery over several decades and personal testimony from a local resident, I've concluded that land cover tools can be used to monitor urbanization in rural communities, but the lack of constant updates from satellites leads to inaccuracies in those monitorizations of these communities. So what's next? If I had an extended time frame, I would expand myself to the entire city of West Columbia, focusing on when these changes happened, when these communities were popping up, and when certain things were disappearing. So I want to give a thank you to all the sponsors who made SEAS this year possible and allowed me to participate in it. And I also want to thank all of the mentors who were there for me whenever we were doing this. So thank you to Ms. Cassie Sofing, Dr. Erica Podes, Andrew Clark, and the special help of Mr. Peter Nelson and Dr. Rusty Lowe, who helped me immensely. And finally, I want to thank Roseanne Smith, who finally reached her dream of becoming a scientist at 74 years old.
Great presentation. So we invite all of the teams that just presented from the Earth System Explorers to turn on their cameras and their microphones. We have questions for several of the groups. We're going to start with team number 8. Question is, other than adding more trees, do you have a suggestion for urban areas to lower their UHI effect?
Yeah, so increasing the amount of vegetation in an urban area is definitely the best way to minimize the UHI effect. So it ultimately falls upon city officials to support infrastructure plans that'll increase the amount of vegetations like trees and parks in cities and urban areas. But also residents can get involved as well by planting things like rooftop gardens, and those can really help minimize the UHI effect.
Also for team number 8, why did you choose Python to make your data sets?
Yeah, there were a lot of different languages we could have used to analyze our data sets, but we ultimately decided on Python because it was what we were most familiar with, especially after using the Python trainings along with Jupyter Notebook provided by the internship.
So for team number 9, what are your thoughts on only choosing data sets from 2018 and 2022?
Well, for our team, we used the data sets from 2018 to 2022 because it was the most plentiful and it worked the best with our analysis and time availability. Thank you.
Also for team number 9, do you anticipate that any trends you found would be applicable to locations past been in? How would you account for differences across geography?
Well, our model is always applicable to any location in the world because it develops a trend based off the differences in geography and utilizes the vectors of vegetation, rainfall, humidity, and like temperature to identify areas with the proper conditions for mosquito populations. But we would say that the differences in geography are actually needed for an even spread to train the model, as similar geographical types leads to an uneven split with the training and testing data sets, which ultimately leads to overtraining in the model, which we saw in ours. And this leads to a significantly lower accuracy when it comes to like a variation of geographical data.
So for team number 10, what criteria did you choose to select your AOI locations?
We just picked 3 that were like in the Houston area because we wanted to focus on Houston. So we picked ones that were like in different areas around Houston.
And why did you choose ArcGIS for your mapping tool?
ArcGIS helped with the mosquito mapping data because that's where citizen scientists can take pictures of their mosquito larvae and post it there. And it gives you specific locations around Houston.
Team number 11. Is there a particular reason that you chose West Columbia as your location for your research?
Yes, it's first off where I live, it's my hometown. And second, West Columbia and its neighboring city, Brazoria, are always tied together when speaking about them. And they were the first capital of Texas. So it was when Stephen F. Austin founded Texas, they were one of the first cities that were made. So depending on how far back I could go, I could further increase my understanding of how it developed.
Great. So this question is for any team that might want to answer. Did you find anything interesting or surprising through your research? Anyone? So we will move on. So the Earth System Explorers is our largest intern project group. A special thanks to the mentors and peer mentors for their dedication to our interns. Your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. Selena and I thank you for your time and your talent that you shared with our student interns. I know the SEAS interns join me in their appreciation for your guidance and advice as they conducted their research. The success of the NASA STEM Enhancement in Earth Science program is determined not only by the commitment and research by the student interns, but also by their mentors and project assistants. Your passion for youth development, STEM learning, and NASA opportunities is to be applauded. Selena and I thank each of you for your time, your talent, your patience, your understanding, and your commitment to all of these student interns. I know the SEAS interns appreciate your guidance and advice as they conducted their research. So thank you all for joining us for day 2 of the NASA SEAS Science Symposium. Please join us tomorrow at 12:30 Central Time as we continue to share the amazing research from the 2023 NASA SEAS interns.